Hello, everyone, and welcome to Science Rendezvous 2022. This is our virtual festival. My name is Dominique, and I will be your MC for webinar 3 of the SR show today. We are very excited to have you join us for our second virtual festival, and we look forward to seeing some very exciting presentations from our special guest speakers today. Could I get the next slide, please? For our agenda, please visit the program schedule on the Science Rendezvous website to see a list of presenters from 10 a.m. till 5 p.m. today. Our website is www.sciencerendezvousoft.ca. You can click 2022 Festival and Program for more details. Next slide, please. Sorry, everyone, if you wouldn't mind just holding on with us while we sort out a few technical difficulties. Perfect, thank you. Before we begin, here are a few virtual best practices. Please post in the Zoom chat. Our presenters will take questions during their segment if there is extra time. And if you have any technical issues throughout the module, please send your questions to uftsr.virtualhelpdesk@gmail.com and they will help you right away. Next slide. And lastly, we would like to give a huge thank you to our partners for their support in making Science Rendezvous possible. Next slide. We will now have the University of Toronto Department of Earth Sciences joining us with their activity, Stories in the Stones, U of T Urban Geotour. As a reminder, if you have any questions for our speakers, please post in the Zoom chat and we will answer them if there is time. Earth Sciences, please take it away.
Perfect, thank you. So I'm going to go ahead and share my screen. And hopefully you can see my PowerPoint. So today we're going to be talking to you about a project that we have started working on. We started working on it during the pandemic to give people options for virtual field trips instead of just field trips that are in person. And one of the ways that we started doing this is actually by trying to get a better understanding of the geology that we actually have accessible on campus. And so the history of Toronto can kind of be sourced through these stones that we actually see in our buildings throughout the campus. And this is a project that's been led by the University of Toronto, as well as the Professional Geoscientists of Ontario Education Foundation. And they are currently working on a geoscience info website that has lots of different virtual field trips all around Ontario if you want to explore and learn more. So to start off, I want to talk a little bit about geologic time. And so for a lot of geologic time, we didn't have a lot of creatures or anything on the Earth. So for the majority of Earth's history, which we're using the CN Tower to kind of make sense of how big and long 4 billion years is, we don't have a lot of life. You've got the Hadean and the Archean, which is just ancient time. So up until about 2.5 billion years ago, we don't see even a ton of rocks forming on the Earth. And then around this time, we actually see the formation of the Canadian Shield, which are some of our oldest rocks in Canada, including here in Ontario. In Ontario, our oldest rocks are up by Hudson Bay. And we started to see the first life during this time. But all of the exciting things that you think about as geologic history, like the rise of the dinosaurs and all of that, don't happen till about 250 million years ago. And then finally, we arrive at this, at the very peak of the CN Tower. So there is a lot of Earth history that has happened before us. And today we're really going to be diving into the Paleozoic, which is between 539 and 252 million years ago. And this is where we start to get big tropical oceans filling southern Ontario, and it would have been a really nice place to live. Similar to modern day Caribbean, nice tropical shallow seas with big coral reefs, but the reefs didn't really resemble what we have on Earth today. So how old are Ontario's rocks? We have quite a range of rocks. We have the oldest rocks in the Canadian Shield, and then our youngest rocks have actually been created by glaciers in the last 10,000 years here in Ontario, especially around the Toronto region. So what does the geology of Southern Ontario look like? This is just a quick overview. You've got your Precambrian rocks. So this is stuff that's older than 550 million years old. We don't get a ton of life or fossils during this time. Things are just kind of starting to evolve. And so that would be our Canadian Shield. And it's important to understand these rocks because any faulting or structural changes in these older rocks actually dictate what happens in these younger rocks. So most of our building stones that we're going to be talking about today come from these lower Paleozoic tropical seas, this blue limestone and the blue shale. And then above the Paleozoic rocks, we've got the Pleistocene glaciations. So those are the glaciations that happened about 10,000 years ago when big ice sheets covered most of Canada and kind of created the Great Lakes. And then finally, we have our present day landscape where we've got our big tall buildings, our landfills, our groundwater. So we really need to understand what's underneath us so that we can get a better understanding of how our groundwater and contaminants actually move through the subsurface. So this is a brief, it's like a generalized map of Southern Ontario. So you've got your Canadian Shield in red. These are really old rocks. And then you got the Paleozoics in blue. And it's kind of a funny pattern when you're looking at a bird's eye view, why we have Paleozoics in London and Hamilton all the way to Kingston, but not up here. But what you can do is if you take a look at a side view of how these sediments actually sit on our planet, you can see that the Canadian Shield forms a little bit of a triangle. And so what happened is the Canadian Shield was already there in place, and the Paleozoics, these rocks, these limestones, these big coral reefs actually filled in the available space. And so that's why they're over here. And you can see they're thicker up towards London. They make up the majority of the Niagara Escarpment that you can see in Hamilton. And then they get a bit thinner throughout Toronto, where they're covered in all these big glacial sediments. And finally, you have them exposed again in Kingston, where we don't have as much of those big glacial sediments. So if you want to learn more about any of the geology of Southern Ontario, there are virtual field trips and story maps on the geoscienceinfo.com website that you can explore on your own, or you can use these virtual field trips to actually visit these places in person. And so that's what we're going to be talking about a little bit today, one of these urban geotrails, specifically the one of the University of Toronto campus. So I'm going to stop sharing this PowerPoint and go ahead and open the tour. So this is, can you guys still see this? Maybe you guys can see my screen?
No.
I can't see your screen right now.
I can share it again. Perfect. Thanks. How about now?
Yeah.
Yes. Right.
Good. Okay. Perfect. So this is the website for the University of Toronto Urban Geo Trail. And you can use this virtually to explore, or you can also go and visit in person and use your smartphone or a tablet to actually see these buildings up close. So you can go for a walk through campus and learn about geology. Toronto's rich history can be explored through these buildings. And so you can use the photos, 3D models and everything to explore as you work through. So right now we have 7 buildings, and the idea is eventually we'll have more buildings, hopefully connecting us all the way to Union Station so that people visiting Toronto can learn lots about the building stones along the way. And so I'll be talking to you mostly about Knox College, which is shown here in number 1. And Knox College is primarily made out of sandstone. And so when we start thinking about these building stones and where the stones came from, one of the first things we dived into was the quarries. And so quarries are locations where we extract building materials or rocks from the subsurface, and we dig big holes and take the rocks out so that we can use them locally. And you can see here, these are some of the building stones that we use at U of T. And it's interesting because a lot of these building stones are actually sourced really close to campus. Rocks are really big and really heavy. So they're not the easiest things to transport. So the more rocks that we can actually get from very close to campus, the better. So the majority of our rocks come from the Credit River Valley area up here, just north of Toronto, as well as the Niagara area. And then as these quarries started to close around the 1930s, then we had to actually extend our search for building stones out to the maritime provinces, out to New Brunswick, to actually find some of these stones. So a good example of this is actually the Sackville Sandstone Quarry. You can see these stones are 2 different colors. This is from the Legislative Building, and after there was fire and they needed to replace some of the stones, the Credit Valley sandstones, that dark red, was no longer available, so we had to use these lighter red stones and try to match as closely as possible. Another interesting example is the Indiana limestone, which I'll be talking about with Knox College. The Indiana limestone is great because these are stones that are easy to carve. And so they were very much worth importing into Toronto because we could use them for decorative parts of the building. So I'm going to go ahead and dive into Knox College. And so this is, I'm going to bring it back to the beginning here. So this is Knox College. It's a pre-recognizable building on campus. And it's been featured in movies and whatnot. And so when you start your geo trail, you get to see what the building looks like. And it'll tell you a little bit about the geology. So the rocks here in Knox College are from the Whirlpool Formation sandstones. So these are white, red, and gray sandstones. And depending on which quarry they come from, they're slightly different colors. So I'm just going to refresh this because it's not loading the next bit. So usually what happens, there we go, is as you move the text, the picture should swap. So the first bit tells you a little bit about the history, that Knox College originally started out on Spadina Circle, but then when it joined and affiliated with the University of Toronto campus, it moved to George Street so that it could be more within the campus limits at the time. Now that the campus limits have extended to include Spadina Circle, it doesn't make much of a difference, but back then it did make a huge difference. And so then there are the 3 different entrances that you can go and get up close to the rocks and take a look and see what you can find that tell you about how the rocks formed. So when you look closely at the entrance to Knox College, this is the eastern entrance, you can see that there are all these stones around the edge that have black on them. These are the sandstones, but they have this black coating on them because of the pollution in the air. They actually end up weathering the sandstones. And then this lighter colored material that's used to do the detail within the entrance, those are those Indiana limestones that are much easier to carve and easier to do detailed work. The detailed work also is more protected. It doesn't weather as easy as we get rain and snow and frost. And so that's why they're used for the decorative parts. And so we talked about it's from the Whirlpool Formation. And then all of these units above the Whirlpool Formation are actually the units that we get throughout the Niagara Escarpment Hamilton area, and then just north of Toronto up by Georgetown. The geology in Southern Ontario is so great for agriculture because of these rocks that we have. We've got these great Queenston shales. These are bright red and gray, and this is actually what allows us to grow things like wine and peaches and all that great agriculture throughout the area. The best place to see the Whirlpool Formation in person, if you want to go, is by the Whirlpool Bridge in Niagara Falls. There's a couple different Niagara parks there where you can see the rocks in the unit. So this is what the rock looks like up close. You've got these tiny layers. So as sediments are laid down, they form layers, which geologists call beds. And sometimes these layers are flat, like you see here, they're horizontal. But sometimes you end up with them on a diagonal line called cross-bedding, which we'll talk about more in a few minutes. So this is an example of that Indiana limestone. And you can see this is a bivalve fossil. So it's kind of like a seashell that you'd find on the beach, but if you can imagine it kind of being tucked in backside into the rock and then filled in with sediment. So you're just able to see kind of the outside of this fossil. But these units are super cool. They're full of fossils. So if you get up and close, you can see lots of things in there. This is another example of that horizontal bedding, but you can see here that some of the bedding has actually started to be eroded away by erosion and different processes. And then this is a different type of rock. So a lot of the steps are actually made of igneous rock. This is a type of granite. And you can see that there are lots of big crystals in this. So this would have been formed by magma in a volcano or inside the earth instead of sediments from rivers and oceans and things like that. And the other thing I just want to point out quickly before I hand it over is most of these buildings include 3D models. And so you can use these 3D models and the annotations on them to zoom into specific areas and get an idea of where you should be looking for fossils. So I don't know how close I can get, but you can see here, this is where you can actually find those fossil fragments if you want to go in person sometime and take a look. And there's one of these 3D models for each entrance. So you could do some exploring in person, or feel free to spend some time exploring the virtual models on your own time. And we're taking any feedback on the tour. So if you have any comments or suggestions, feel free to put them in the chat and our moderators will pass them on to us. Otherwise, I'm going to turn it over to the next presenter and stop sharing here.
Yep. Sorry, so I'm Jonathan. I'm just going to be talking about some more of the buildings that I think were pretty interesting. One of them being the legislature building. I've never been inside, but I walk by it every day, and I thought it would be nice to know about the place where we pay our politicians to enact laws and stuff like that. And so we've already actually seen some of the Rocks Legislative Building before in Katie's presentation, but this is the whole building. Is the view from the south at Queen's Park. There's a pretty funny story about how it got built. It turns out that the top two designs, the government hired a man named where's his name listed? Richard Waite to just help decide which building design we should go with. And he decided that neither design was really possible. And so he hired himself to do the building design. But it's a beautiful building, so you can't complain. It's got a number of different entrances. So there's the main entrance. Like I said, I've actually never been inside, but I've walked. You might have walked, or I've walked through many of them. And luckily, when we're looking at the rocks, we don't need to go inside the building. We can just look at the outside. So most of these rocks on the outside are these red whirlpool sandstone. So Katie mentioned that the whirlpool sandstones, they come in various colors from white to gray to red based on what quarry you're getting them from. So they have these red ones for the legislative building, that red color coming from a lot of iron oxides, the same thing that's rust. And one thing that Katie mentioned, this idea of rocks being forming in these layers. So we have these really nice horizontal layers or beds, but some of these rocks also show these cross bedding. So here the rock layers are going in these nice diagonal lines. This is the same image Katie showed earlier, this idea of like, just like you're trying to color match bricks and you might find it impossible, the government also found it impossible to color match their rocks when they had a fire. And so we see these two different kinds of rocks, two different sandstones, the Sackville sandstone from New Brunswick, and then the Whirlpool sandstone that the rest of the building is made out of. And one notable feature of these Sackville sandstones, the lighter ones on the right, is they do not show any cross bedding. They only have the horizontal beds. This image is missing. Some parts of the building are not made with the same kind of rocks. So you'll notice that these rocks up here are red, but this layer at the bottom, this is the beginning of the basement. The basement is constructed with gray limestone. So it's the same kind of rock that makes up when you have lime scale buildup in your bathroom. It's the same mineral composition that makes up these rocks here. One interesting thing that happens with a building like the legislative one that we care about is maintaining it, making sure that the rocks, because the rocks do get damaged by wind and rain, and especially acid rain and salt and stuff. And so this image is a little bit difficult to see, but exposed faces end up damaging much more quickly than hidden ones on underhanging windows or under roofs. And so we end up having to go in and replace some bits of rocks or entire chunks with new rocks to make sure that the building still looks good from the outside. So in this case, some of the rocks are replaced with Haldenby sandstone. And these ones are notable in that when you get really, really up close, you can see that the individual grains are much, much smaller on the replacement rocks. We're actually going to skip this. Another example of the weathering or the damage that happens to these rocks is just like the underside of cars getting damaged by salt in the winter, these rocks get damaged by salt in the winter. So it ends up happening that you can get the outside of rocks being damaged by wind and rain, and you get these interesting weathering patterns. You also get salt or road salt dissolving in water, washing up against the sides of the rocks. The rocks are porous, so this water like penetrates inside the rock, and then the salt recrystallizes inside and ends up kind of like breaking the rock a little bit from the inside. It's most notable. You can actually see the salt, this sort of like white stuff here and over here. It's very noticeable on the bottom level of rocks, the rocks that are directly touching the ground. So it's definitely maintaining a really old, large building actually can be very difficult. And you have all of the same worries that you have at your home or your car. And that is that. I'll talk about the other building I wanted to describe quickly, Trinity College. I think it is a beautiful building. The chapel specifically is gorgeous, and there's a really nice picture of it. And I want to talk about this building also because it uses some interesting limestones. So this is the picture of the inside of the chapel. It's too bad we're missing the top, but it is a very beautiful building. So this is the outside. These are the same whirlpool sandstones as before, and you'll notice that they're not as red. So this is like another example of the difference in color. You can get the same formation, the same whirlpool sandstones, but they look slightly different. And this has to do with the different amounts of minerals or iron oxides inside of them. This is what I wanted to talk about. This is some of the floor tiles that are used in the chapel. So these are called Italian travertine. So usually limestone is made in shallow sea areas where there's lots of little creatures that make calcium carbonate. Calcium carbonate is this, usually when you hear the words lime, lime scale, limestone, it's related to this mineral calcium carbonate. So you usually get in these shallow seas where there's lots of little creatures that make shells like coral or mollusks out of calcium carbonate, and they're the building blocks of these rocks. But this limestone, Italian travertine, is special because it's limestone that has formed not relation to biotic or creatures at all. It's just very heavy concentrations of calcium carbonate from waters deep within the earth, and it comes out at hot springs I think hot springs is actually the most common one. And so you just get a huge concentration of calcium carbonate, the water evaporates, and you get sort of like a natural, not natural, but an abiotic, so not life-related formation of limestone. And people like it because this is exactly the same process that happens in your bathroom sink or in your taps when you get lime scale buildup on your faucets and stuff. It ends up forming a really nice pattern. It's very dense looking. It's lots of layers. It just looks very pretty. It's just a little bit special. And I'm going to stop there and hand it off to Tasca to talk about some stuff.
Hi, everyone. My name is Tasca. I'm a teaching professor in the Department of Earth Science. And I would also like to talk about one of the buildings. So let me share my screen. Give me 1 second. This one here. So I want to talk a little bit about University College and specifically some of the history and the traditions that go on at the university. So University College is one of the oldest buildings on campus, and it's quite beautiful inside and outside. And like all the historical buildings, it also has a lot of nice building blocks that tell us about the geology of Ontario and surrounding areas. All these buildings on campus, all these historical buildings were built based on different architectures. So you'll notice that if you're in architecture or art or art history enthusiast, you'll notice that they are built with different styles. There is the Gothic style. So Knox College is built with the Gothic style, and it's also quite beautiful inside. There is also Convocation Hall that is more of a modern or Renaissance, I believe. And then there is University College, that is also a different style. Here you'll notice that there are different rocks depending on what the rocks were used for. So you have the big blocks here, and then you'll notice that the entrance has a lot of carving. So let me go down to show you a more detailed picture. So this here was made out of the Ohio sandstone because it was easy to carve. So the architects that built all these buildings had freedom to choose the style that they wanted to use. But more interestingly, the masons that worked on these carvings also had freedom. Specifically, University College, if you look at the entrance here and you look at these columns, you won't find two columns of the same style. So the masons got to pick what design they wanted to put and what design they wanted to carve into these columns. Another nice piece of detail at University College is that you'll find these little corners at the edges of doors and at the edges of windows, or at the top of the roof and sort of at the corners of the buildings. And you'll notice that there's either a leaf or a face or sort of a figurine, and they're all different. There's no two columns or there's no two corners that are exactly the same. So definitely, if you are on campus and if you're in this area, definitely check these buildings out and see if you can find two corners or two columns that are exactly the same. Another nice tradition that we have at the university is the convocation. This is the time when all the graduates convocate and to receive their degree, to officially graduate. And what is the tradition is that all the graduates get together in University College, and they sort of get dressed and they wear their gown, and then they walk across University College. Right now there's a lot of construction, so they sort of have to go around, but they walk across University College to this building here, which is Convocation Hall. And if you've been in the center or around King's College Circle, you would have noticed this iconic building. It's, I believe it's one of the most photographed buildings on campus, aside from University College. And so all the graduates will walk across and enter this building, and they are actually sort of escorted or guided by the professors that taught them. And really nice part of this is that the professors will wear their gown from when they graduated from their university. So you would have professors with very elaborate gowns, different hats from all over the world. So you'll have, with feathers or big designs or sort of really nice fascinators, and they all guide the students into this building. In the building, they are met, or they are introduced to the parents of the students and also to the audience, and they are presented in front of the chancellor. And the chancellor, depending on the degree that they are receiving, the chancellor will either, the graduate will either kneel down in front of the chancellor, and the chancellor puts the robe, the graduation robe, around the student or the graduate, or they stand in front of the chancellor. So if you're getting a PhD degree or a doctoral degree, you would stand in front of the chancellor, and the chancellor also stands in front of you. But if you're getting a master's, or sorry, a bachelor degree, then you kneel down in front of the chancellor, and the chancellor's assistant puts a robe or sort of the collar around the graduating student. So this is a really nice tradition that the university has. And the way the university lets the entire city or the surrounding area know that today is convocation or graduation week is by playing the organ in the soldiers' chapel. So for about a couple of hours, the organ in the soldiers' chapel is playing, and this is how the university lets the city or the surrounding neighborhoods know that today the graduates have convocated to receive their degree. So this, if you're on campus sometime around June or early June, definitely look out for this procession, and also for the organ playing. I'd also like to share what we do in the department. So this is, let me change screens here. Okay. So we study as geologists, we study the earth. And one of the ways we study the earth is or what happens, how mountains are built, for example, or how volcanoes occur, or how, for example, travertine is formed, is through analog models. And what analog models are, very simply, they're a physical model of a mountain range or a volcano, and we actually see how they are formed. So it's a mechanical model of how these geological processes are formed. The oldest analog model is by Cadell, and this was in 1888, and we still today use the same process more than 100 years later. The first models were built out of natural material, clays, different types of clays and different types of sands. And what he's doing here, he's basically taking these layers of sediment, or what he is using as layers of sediment, and he's compressing it to form a mountain range. The reason why this idea came up to build analog models was from actually Scottish geologists. When they went into the field, a lot of them were also farmers, and when they went into the field or into the landscape, they noticed that a lot of the sediments were not horizontal like they would form naturally, but they were actually folded. So they wondered, why do we have all these folded sediments when all the sediments that sort of form naturally when you have deposition of sand or silt or mud, they sort of settle in horizontal layers. So why do we have these folded layers? And so they came up with the hypothesis that maybe there is something that is causing these layers to be folded. So there must be some sort of force or compressional force that is folding these layers. And so they decided to make these models where they actually took layers of sand and clay, and they pressed it together to form these folds. But the important thing is, how do we use these models to compare it and to study natural geological processes? So the idea behind is that everything is scaled. So for example, if you were to look at an architectural blueprint, let's say you're buying a house or you're building a house, and you have the blueprints of a house. You'll notice that on paper, everything is scaled to a smaller version of what it is in reality. So on paper, 1 centimeter is actually 1 meter, maybe in nature or in reality. The same way we use the exact same scaling in analog models, where we scale not only for length, so not only for, let's say 1 meter is maybe 100 kilometers in nature, but we also scale for physical properties of the different types of rocks. So for the density, for the viscosity, for basically the rheology of the rocks. And we also scale for time. So a mountain range, let's say the Himalayas or the Andes, took about millions of years, somewhere between 40 to 50 millions of years to form. But in our lab, this same process takes about 1 hour or 2 hours. So we also scale for time. This here on the right side is a nice cross section of the French Alps. So you can see all the different rocks, and a cross section is simply a slice into the earth. So if you were to compare this to a cake, let's say a birthday cake with different layers, the top of the cake would be the surface of the earth, and a slice into the cake where you could see the different layers of the cake would be the cross section. So here, this is a cross section into the earth where you can see the different layers of and different rocks. Similarly here, this is an analog model. This is a cross section of an analog model where we again used different sand or different colors of sand to indicate as an analog for the different rock layers. And this here actually is a finished analog model that shows a nice mountain range, very similar to this cross section of the French Alps. The materials we use to create these models can be anything from any granular material, as long as it scales properly to the natural rock. So sand, flour, sugar, different types of sands, so granite sands, silica sands. We also use different viscous material, because the mantle or deeper in the earth is actually a viscous material. So we also use honey, silly putty, different types of gels to form the mantle or the deeper earth. So this is below 20 kilometers, 10 to 20 kilometers. This is what the lab at the University of Toronto looks like. We have this box here where we create our models, and depending on the model, the box is different. And this box specifically is called a sandbox. There are several cameras to control the forces that are acting on the model. And we have these high resolution cameras. And these are special cameras that record how the mountain is formed. And so we use this data to understand what happened during this process that the mountain is being formed. So we have all these, the box, control stations, and then the cameras, and a motor to push the ends of the model to form our mountain range. So here I have a nice a video of formation of a mountain range. This is a huge box that is about 3 meters long. There is a back wall over here, and the sand, there are 3 different layers of sand, and later on you'll see another different set of layers coming in. The sand is sitting on a conveyor belt. So this conveyor belt is the same conveyor belt that you see at baggage claim in an airport. It's the same material, and the conveyor belt is moving towards this back wall. So I'm going to play this, and while the conveyor belt is moving towards the back wall, you'll see the formation of different layers sort of being under thrusted under other layers, or younger or older layers, sorry, and you'll see the formation of a mountain range. So you'll notice that the mountain range is beginning to grow, and soon. So you'll see how the mountain range is basically uplifted. And now you see the addition of a different set of layer. And this second set of layer continues to uplift the mountain. And then you also see, I'll play this again. You also see what is formed here are faults. So these are the faults that would cause an earthquake. So in this mountain range that took about, this is a fast forward or fast forwarded version of this model. But this model in total took about 50 minutes. But in reality, this mountain range would take about 50 million years to form. Okay, I believe that is the end of our time. So if there are any questions, please feel free to ask.
Thank you so much, Katie, Jonathan, and Tasca. I do have a few questions here for you. The first one hopefully will be relatively easy, and anyone is welcome to answer it. What is your favorite type of rock or stone and why?
I would guess we probably all have slightly different answers for this, but I definitely like sedimentary rocks. More fine grain is better because as a paleontologist, that's where we search for fossils.
I'm maybe a little bit fancier. I really like gemstones, and those are definitely rocks. So I like opals. Opals are my favorite rocks. I love the shiny color, the rainbow, the interesting refractive light properties of opals.
So I would say, since I'm a structural geologist, I like anything that shows wispy, wavy, ductile structures. But I also do like gemstones. Anything that has color. We have so many beautiful gemstones in the world. So if you're picking out a ring, definitely look at gemstones, not only the diamonds.
That's some great advice, and those are fantastic answers. Thank you. This question might be more geared towards Katie or Jonathan, but you both kind of talked about how rocks can be weathered and salt can break them down. Do you guys ever look at these weathering patterns on the rock to get a sense of what kind of weather these rocks have been exposed to?
So sometimes we use, especially with older rocks, so more modern rocks, especially things that are used in building stones, we can look at salt and weathering that way. But with even older rocks, a lot of the rocks that I work on are almost 1 billion years old. We actually use the chemistry of the rocks and how the minerals have actually changed through time to get an understanding of how weathered they are, because there's certain minerals that are really stable over long periods of time. And then there's other ones that are less stable, and we can use those ratios to date the rock as well as try to understand how weathered it is.
Oh, that's great. And this kind of transitions really well into our next question. One of our attendees asked what the difference was between a gemstone and a mineral.
So a mineral is a very specific chemical and like physical structure, or the organization of those elements and minerals. And gemstones are made up of minerals, often of one very specific mineral. Usually gemstones are very pure, and the way that they look in our jewelry is we have cut and polished them to give them a specific appearance, to shine or refract light so that they sparkle. So yeah.
Thank you. And just a few more questions. For the analog models, is it difficult to scale those, or is it pretty easy?
No, it depends on so the sand model that I showed you was very easy because it's only one material. But the more complex you make the model, so if you have more than one material, let's say you have honey and sand, then it becomes a little bit more difficult because both of them have to be scaled. So if you have 3 or more materials, then it becomes a little bit more difficult. So the more complex you make it, the more difficult it is to scale.
I can only imagine the old times, them having to do it all by hand must have been quite difficult.
Yeah, for sure.
Thank you. We have another question from the audience. Someone is wondering how diamonds are made.
So I don't study diamonds, so I can give you a brief overview. So most of the diamonds we find are in the Canadian Shield. They're like really old rocks that we can find these diamonds in. And diamonds come in a specific type of rock. They're called a kimberlite. And what they are, they're like, you can kind of imagine them as pipes or conduits that like connect the deep part of the earth, the mantle, to the surface. And so whenever you get that like really deep stuff coming up from the earth, that's where it's hot enough and you have the right composition to actually make diamonds. Tosca might be able to comment further, but that's my understanding.
No, that's exactly it. That's how diamonds. So diamonds are formed deep in the earth because they need a certain amount of pressure and temperature. And so you see all these puns and jokes related to, let's say, coal, and then it turns into a diamond, or you're a diamond in the rough. The reason why is because they are exposed to a lot of temperature and pressure there. And so they are formed deep in, and this is where you would have these temperatures or pressures deep into the earth. But the way they are brought to the surface is through, like Katie said, kimberlite pipes. And they're basically, like she mentioned, pipes or conduits that bring the diamonds to the surface. So the diamonds that you find, say, let's say in riverbeds, or is basically these eroded parts of the kimberlite that have been washed into the rivers and so on.
Fantastic, thank you. We have time for, I think, one final question. You guys were showing us some beautiful, wonderful buildings. How long do you think it would have taken to construct most of those buildings?
So there's a lot of funny stories actually about how the buildings were constructed on campus, and you can read more of them in the tour, but a lot of it has to do with like where and when funding became available, and then when and where funding kind of disappeared. So a lot of times they'd start building a structure because they knew they needed the space, but then something else would happen, like World War I started or something like that, and all of a sudden the money was gone. So you have to wait a little bit while and kind of build onto pre-existing structures. And that's why we have lots and lots of extensions at most universities and big buildings, because you have to build when the stones are available, when the money is available, and when there's people available to work on these buildings, if that makes sense.
Fantastic. And if you guys wouldn't mind just reiterating once again, where can we find more information about these tours if we would like it?
So the tours are posted on the geoscienceinfo.com website. I'm not sure if the building stores tour is up there yet, but it will be up there within the next little while. But there are lots of virtual field trips already on there, from Manitoulin Island, Kingston, Niagara Falls. So, and they have driving directions and everything in case you want to go in person and not do the virtual version. So yeah, definitely check out the geoscienceinfo.com website.
Perfect. And once again, thank you, Katie, Jonathan, and Tasca. That was a wonderful presentation, and I definitely learned a lot. Thank you so much.
Thank you.
Thank you.
All right. So thanks again. And now we are going to move on, and please join me in welcoming the Department of Physiology with their activity, Discover Human Physiology, How Our Bodies Work. As a reminder, if you have any questions for our speakers, please post them in the Zoom chat or use the Q&A Zoom function, and we will answer them if there's time. Physiology, please take it away.
All right, good morning, everybody. Thank you for having me today. I'm just gonna get set up here and share my screen. Okay, and then can I just get a test, because I'm going to be asking some questions, so please feel free to put your responses either live, so you can unmute yourselves, or throw them in the chat. But with the chat function, can I just get somebody to just use it so I can see it, make sure I can see it on my screen? Maybe just put like a hi or something.
Riley, our attendees I don't believe they have privileges to turn on mics and go live.
So no worries there. Then on the chat though, could we just make sure that that's working? Just so if I ask a question during the presentation, if there's going to be an ability for people to get a response. If not, no worries, we can just kind of get started, but I just want to make sure beforehand.
Perfect, so I can pass on some answers to you from our Q&A section.
Do you mind doing that? Or I can also just go on.
No, that's perfect. That works.
Okay, amazing. Okay. So hello, everybody. My name is Riley, and I'm from the University of Toronto's Department of Physiology. And today we're just going to run through maybe just a quick couple of activities where we're going to teach you a little bit more about the human body and how it works. So as we get started, make sure I can change the screen. So the first kind of thing I have to ask everybody is, does anybody know what the word physiology actually means? Perfect. Yeah, use the Q&A function there. Awesome. And I can see that. So if people type their responses into the Q&A function, then I can see them there. But if there's no responses, we can get started with later on. So the word physiology simply means it's the science of life. So when we study physiology, we study how organs function and how they work together to give us the opportunity to eat, sleep, talk with our friends, do some exercise, and many more different activities. But I guess one of the things, awesome, yeah, the study about the body. I just saw that response there. But I guess one of my also preliminary questions to everybody: does anybody have a favorite organ and favorite organ of the body and why, or anything they may be? I guess maybe a better question too would be, does anybody have a specific organ in the body they want to learn more about as well? The heart, awesome. Anybody else? Heart, liver, cool. And does anybody have reasons why they think these organs are the coolest, or are they most interested in them? No? Okay. Sorry, I can hear there's a vacuum going on in my background. Give me 2 seconds, I'll be right back just tell them to be quiet.
And while we're waiting, please feel free to put your answers in the Q&A section as to why you have your favorite organ.
So sorry about that. Awesome. Yeah. So you heard the liver can regenerate. So we're going to talk about that definitely in our talk today. But we'll keep moving on right now. So this is kind of the something known as physiologists will call the hierarchy of life. And at the bottom of this pyramid, this life pyramid that we have here, kind of the building blocks of life that we have are something known as our genes. And these genes are really just a set of instructions that our bodies can use to make certain building blocks of life called molecules. These molecules then kind of come together and organize themselves in certain ways to fill out organelles. These organelles are actually specific units within our cells. If some of us will be familiar with what cells are, cells are the kind of basic functional units, the part of our bodies that are really doing the work at the kind of most basic level. And these organelles are going to populate and fill in these cells. And as I just said, the cells are that basic unit that's going to be carrying out life. We as human beings have billions, if not trillions, of cells in our body that are all working together to help us function. But the groups of cells will come together to form something known as tissues. And then, as I just asked you guys a little bit earlier, we talked about some organs. So different tissues are then going to come together and form organs. And we talked about a couple of them already. We talked about the heart. I think somebody mentioned the liver. The brain as well is also an organ. So these groups of tissues are then going to come together to form these kind of larger, more functional organs that we can hold in our hands. They'll then form organ systems, which is kind of the second highest pillar of life. And then finally, this top level is the organism itself. And that's what an individual human being would be. So this is just kind of the escalation of life from the building blocks right at the bottom, all the way up to the complete full human being at the top of the pyramid. So can anybody tell me what we're looking at, what organ specifically we're looking at on this slide right here? Does anybody know? The heart. Awesome. I'm seeing a bunch of responses here. Perfect. So I guess, so we're looking at a heart on all these images actually. And I guess the kind of bonus question would be, do we know which one would be the human heart? Is it going to be the kind of teal color, or the one indicated by the teal color, one indicated by the orange, the white, or the red? Perfect. I just saw teal. Awesome. So that's a great response. Whoever was able to determine that. This image on the over here is actually going to be the human heart in this teal color. And what's interesting is that this orange one actually is a heart that a fish uses to pump its blood. So a heart across different organisms, right? And that's what we would classify a fish as. It's a different organism than a human being. Hearts are very functional, and they're needed in all kinds of different bodies in order to pump blood and move blood around the body of whatever organism the heart is in. So this is a fish heart, an example of what a fish heart looks like. This is actually an example in the white here of a chicken heart. And this massive structure on the right-hand side here that's noted in red is a heart of a blue whale, which is the largest organism that exists on Earth today. And what's I also find fascinating is that, right, this is kind of, they're all at similar sizes, but if we look at relatively, so comparing the sizes of these hearts between the different organisms, we can see that this is eventually what they end up becoming, right? The whale heart is so much bigger than even our human hearts that I have inside of my body, that everybody has inside of their bodies. And then we have the tiny relative fish and chicken hearts compared to these other two larger organisms. All right, and yeah, another just cool kind of fact here is that we can actually fit, especially if you're a little bit smaller, we can actually fit inside of a whale heart. You can crawl through the great vessels that lead into and out of the big chambers, but that's how big these things are. They're very, very large. And yeah, I think it's the average size of a blue whale heart is 400 pounds. It's very, very heavy. Yeah, so if anybody has any questions, please feel free to ask throughout. I can see the Q&A chat, so no problem there if anybody has, but I'll just keep moving on, and feel free to just ask any questions in the chat. Okay, so that was just a kind of brief opening exercise that we're going to go through today, but I now have 3 more kind of more specific activities that we're going to work through. First of which is going to be something known as rapid reflexes. So we'll then move into how we make muscles. And then finally, we're going to finish off with some microscope images. So I got a question in the chat here. It says, what size is a baby blue whale heart? That's a good question. It's definitely going to be smaller. So I'll go back 2 slides here really quickly. But this would definitely be an adult size blue whale heart. So if anybody's seen Finding Nemo, the big whale at the end of the movie, if I just blew up for anybody, I'm really sorry. But the big whale at the end of the movie, that's the kind of size of the heart that would be in that organism. But it would be much smaller inside a baby in a baby blue whale heart. I got another question. So do whales have fat accumulated on their hearts like humans do? That's a really great question, actually. So I'm not 100% sure about, so different organisms will use different energy sources. And a reason why that humans have fat on the outside of their hearts is so that it has a direct access to available energy that it can use to keep beating. So it's going to be my intuition is telling me that yes, whale hearts are going to be wrapped around in fat because they can use that for their energy supply. Another interesting thing about whales is that they have a much thicker layer of fat than humans do on the outside of their body. So not necessarily directly around the heart, but entirely on the outside of their body. And this helps them have insulation. So if anybody's heard of whale blubber, that's essentially what it is. They have a thick layer of fat on the outside of their body that helps retain heat in the cold water of the ocean. Okay, but getting into our first exercise today, which is rapid reflexes. So does anybody know, oh, sorry, I just kind of gave it away. The first question is, does anybody know what a reflex is in the body? I'll give people a second here to type their response. Anybody have any ideas what a reflex is in the human body? Okay, no worries, we'll keep moving. So a reflex is can you quickly react to something like dodging a ball coming towards you? Okay, awesome. So that was a great response. Thank you for putting that in there. So the response was that when you quickly react to something like dodging a ball coming towards you. So that is that's a very good answer, but what we're going to actually realize here is that there's a difference between a reaction time and reacting really quickly to something and actually a reflex. And the key difference is that it's involuntary. A reflex is involuntary. So when we think of a reflex, it is an involuntary and nearly instantaneous movement in response to a stimulus. And the movement is so quick that it actually occurs with a recognition from our brain. Now, we may be familiar with a common reflex that's tested, and that is the patellofemoral reflex, where, especially in a doctor's office, for example, when you go in for your annual checkups, they may get that little hammer out, or may even use a pen, and they'll hit this region of your knee, kind of right above that bony part of your leg bone, and they'll look for it and look for a response. What they're checking right there is something known as the patellofemoral reflex, and it sounds like a big word, but all that's talking about is just the two bones kind of where the reflex takes place at. There's the patella, which is kind of the kneecap bone, and then there's the femur, which is the bigger bone at the top of our legs. But essentially what they're testing is that they'll hit this area of the skin, and due to the fact that we have sensory receptors, we have tiny little receptors that are embedded in this area of our skin, the nerve can sense that there's the contact of either the physician's hammer or their pen on the skin, and without actually sending anything to the brain, the leg muscles are going to contract, and they get this kind of a jerk response. So that's the key difference between something like that's the key difference between reacting to something coming towards you like a dodgeball, or just having that kind of involuntarily very quick movement of responding to simply just a tap on the leg. That there's really no brain control that goes on. And if we look at this is just a kind of a closer schematic that we can see. But when we have this hammer, right, that's kind of where the doctor would be applying that pressure. They're going to strike this area of the skin with the hammer. There'll be a sensing of this kind of change in the length of the tissue around the knee. That'll send a very, very quick signal to the spinal cord. That's what this structure is over here. But without sending information upwards towards the brain, we'll actually see the signal stay within the level of the spinal cord. So they'll go into the spinal cord and come right back out of the spinal cord and go right back to the muscles that were affected in that area. Again, causing something, a very rapid and involuntary response to a stimulus. So reflexes are tested not only at the patellofemoral level, right at that knee spot that we just saw, but reflexes are also very important for newborn babies as well. And in fact, if for all of us that were born, if we were born at least in Canadian hospitals, one of the standards of care that doctors will do for newborn babies is test them on specific reflexes. And as I said earlier, these reflexes are really important because our brain isn't responsible for making them. And when we're looking at newborn babies that are still developing and that don't really have control or the ability to speak, for example, these involuntary reflexes help them stay alive in that early time between being born and being able to ask for things like food or clothes or making sure that they're comfortable. So this first reflex that we can see is that this grasp is a grasping reflex. And if anybody has younger siblings or knows somebody with a newborn baby, one of the cool things that they just love doing automatically without their brain really instructing them to is that if you place a I don't know, finger-shaped object near their hand, it's instinct for them to grasp it. So whether it's a pen or whether it's, like I said, a human finger, they love grasping things that come towards them. So I got a question here. Why do we use reflexes? I'll come back to that one once I get through this newborn reflex slide, okay? But looking at the next reflex that doctors commonly test is something known as the Moro or startle reflex. And this is one of the things that I found very interesting. I've done a little bit of work working with doctors in the hospital, especially with newborn babies. And one of the things that you see them do is that they'll try and startle the baby. So they'll this will be right after the baby is born, and they'll kind of very safely drop the baby while in their hands, and to see if their arms spread out and their legs spread out like this. And that's a very healthy reflex to have as a baby, and again is one of the reasons why it gets tested. The next reflex is something known as a rooting reflex, and this reflex happens when if you brush the side of a baby's cheek, they tend to move towards that side, right? And that's very important for things like breastfeeding or just feeding early on in the baby's life, where again they can't necessarily say that they're hungry or grasp the whole bottle with their hand, but they can at least turn towards wherever the food is coming from. And finally, the last reflex is just kind of fun to say. It's the Babinski reflex. And this Babinski reflex is important for helping actually train the babies how to walk eventually. So this reflex takes place in the foot. And if you had, so for my foot example, if somebody got a feather and they brushed the inside of my foot, if my hand's my foot, for example, if they brushed the kind of palm of my foot would kind of curl in, my toes would curl in. What we see with babies, on the other hand, is that they actually, when there's a stimulus on their bottom of their foot, they actually spread out their feet. And this is thought to be related to the fact that babies don't know how to walk yet, and they need to learn how to walk so that every time they put pressure on their feet, they're training their toes to spread out, to have that proper walking mechanics. But going back to this person's question in the chat here is, why do we use reflexes? So this is these baby reflexes, as I kind of just said, is that these are very critical that babies have these functioning reflexes when they're born. And it's simply due to the fact that there's a delay when a baby's born between them being able to be mature enough to ask for things or to say things like they're hungry, they're upset, or they're cold. And these reflexes help bridge that gap, help the baby survive in these early phases. Now, reflexes that affect us right now, for example, like older adults, we're actually going to see a couple of examples on this next slide. So I have another question here is, what's the point of the startle reflex? Why do they stretch out? So no, that's a good question, and it's going to be answered on this next slide here. But one important thing before we move on is that newborn reflexes actually disappear within the first couple months of life. So these reflexes are the grasping reflex, the rooting reflex, these Babinski reflexes. These will all be present in the first couple months of life, but they actually disappear when the baby becomes 1 year old, 2 years old, 3 years old. These reflexes stop being a thing. And that's just because, again, the baby no longer needs these reflexes, and they're no longer beneficial for the baby to have. So our bodies just naturally stop making them a priority and stop having them stop doing them naturally, if that makes sense. So other reflexes, and this is going into that starting reflex as well. So I have another question here. Do we develop any new reflexes? That's something I am pretty confident saying no. We don't develop reflexes as we go on. We can become very reflexive in certain things. So for example, this is kind of a tangent, going off on a tangent here a little bit. But again, the question was, do we develop new reflexes as we get older? My immediate response is no. This answer is that we don't develop them. But in terms of training our reaction time, training our ability to react to things, we can practice certain tasks so much that they can be described as reflexive responses. So for example, hockey goalies, for example, they'll do different reaction time training work to get good at blocking pucks from all different directions. And they can train that and get better at that, but it's not necessarily a reflex, because again, they're telling their body to go and react very quickly, as opposed to just having a involuntary response to different things. But other we have today, going back to this exercise here, we have something known as hypnic jerks. And if anybody is familiar with this, it's that feeling when you're about to fall asleep that you kind of feel that you're falling and then you suddenly start awake. And going to the question of what's the point of the startle reflex? Well, that moral reflex or startle reflex that we talked about on the last slide with babies, this is a very similar reflex that occurs in adults that we can see in adults. And one of the cool things about this reflex is that scientists think that it goes all the way back millions and millions and millions of years ago, when human beings didn't look like we did today. And we actually were very similar to our chimp ancestors or other primates that are somewhat genetically similar to us. And where did those primates live when they were developing? They actually lived high up in trees, and they would never sleep on the ground, but they would sleep high up in branches of trees. And what scientists believe this hypnic jerk kind of reflex comes in is that if the body senses at all that it may fall out or that it's off balance, it's going to startle you to wake you up so that you don't fall very high out of the tree. Otherwise, if this reflex didn't occur, all of our early ancestors that were very similar to chimps and early primates, they'd be falling out of trees while they were sleeping, and you would get hurt that way to 100%. So they think that the startle reflex really comes out of that shared evolution with primates that we had. Does that answer your question in terms of where the startle reflex goes? If it doesn't, please ask it again, and I can be a little bit more clear. But just checking the other questions we have here. Do we develop new reflexes? We already talked about that one. And then, is it possible to keep baby reflexes for your whole life? And that's a good question. From my understanding of reflexes, they always go away. So unless you're continually training these reflexes or continually having that stimulus that results in the baby's reflex, for example, the moral reflex, they tend to just go away when the body doesn't need to use them anymore. But if you kept enforcing it daily, or even multiple times throughout the day, for example, then you can maybe maintain it a little bit longer. But the majority of these reflexes that occur in babies are going to disappear within the first couple months of life. And can we improve our reflexes? Again, that's a very good question. What I would say, though, is that it would go kind of to my point earlier that we can train to be reactive to things, but we can't really train our reflexes. And it's because of the fact that our reflexes are involuntary. Our brain has no control over whether or not our leg jerks when we have that patellofemoral reflex, for example, or my brain has no control over whether or not I jerk awake when I'm about to fall asleep. Whereas when we're looking at reacting to different things and like, for example, dodging a dodgeball that comes our way, or being able to quickly react to a puck coming our way if we were a hockey goalie, that's training your reaction time and training it's essentially doing muscle training and doing different exercise training, whereas reflexes are more so a natural phenomenon that the brain has no control over. The last kind of reflex that I'll share with you today is not a human reflex, but it is something that people may be familiar with online. And again, this goes back to that kind of evolutionary link to some of these reflexes that go back hundreds of thousands, if not millions of years. And this comes in the form of cats and cucumbers. So it's a little bit of a cruel trick, but there's a lot of videos on YouTube or online that show cats having an immediate reaction to cucumbers or pickles or other kind of cylindrical green shapes. And what scientists have been able to determine is that this kind of startle response, right? It's a reflex response. The cat is thinking, and then boom, reacting. They're getting startled. This again, reaction response was due to the fact that a major kind of beef that exists in the animal kingdom is between cats and snakes. And for thousands and thousands of years, they have been going back and forth between each other. And that eventually the cats that were able to have this kind of startle response to seeing something that looks like a snake, due to the fact that, again, that snake, if they wanted to eat the cat for their dinner, would immediately grasp out, but the startle response to immediately seeing the snake allows the cat to dodge that first strike. and just increase its ability to survive in the environment. So that is, again, just an example of a reflex in other organisms other than humans. So does anybody have any further questions on reflexes before we move on to the next section? Okay, I got this question here. What if you were born with no reflexes? So that's one of the reasons why, that's a very good question. And that's one of the reasons why the doctors test these babies for the reflexes right when they're born, and it's to see if they have these reflexes or not. If baby doesn't have the reflexes, then it doesn't. They're not going to be set back in many different ways, but what it requires much more care early on in life of that baby. So the parents are going to have to be much more vigilant of the baby to see when they might be hungry, when they might be sad, when they need to get their diaper changed, just due to the fact that there's less information or less of an ability for the baby to less of an ability for the baby to request different things and to make sure that it's getting the optimal amount of nutrients in that early part of life. So I got one more question here. If reflexes do not involve the brain, why can conditions of the brain affect reflexes? Awesome, that's a very good question. Okay, so I guess my follow-up question to you then might be, what conditions have you heard that the brain can affect reflexes? That would be my first question. But going back, I guess we can go back quickly to this slide that I had here. A true reflex, right? So something that we're talking about when we talk about this involuntarily and nearly instantaneous movement. If there's anything that was going on in the brain in terms of a condition-wise or disease, it would not affect this patellofemoral reflex. I can say that pretty confidently right now. What may be going on if you're seeing other reflexes affected, one, they may not be those true reflexes, right? If you're looking at, again, your ability to react to something coming towards you, again, you're seeing the stimulus, your brain sees the stimulus, and then it's telling your hands to go up. It's not necessarily a reflex in the sense that this patellofemoral reflex is a reflex, right? Where you just have a stimulus at one point of your body and it triggers a local or same kind of area response. Whereas again, when the brain is having an influence on reflexes per se, they may not be true reflexes, or the condition, or you may have a condition that affects both the brain and also the peripheral nervous system, or the peripheral nerves that are in our hands and not necessarily in our brain. So I hope that answers your question. If not, though, please just ask it again. And then I got one more question here, then we should probably move on for just the sake of time. If you get cut or hurt, what is usually the first reflex that you will have? Okay, so that's a good question too. Cut or hurt is a little tricky, but for example, like touching a hot plate or touching a hot stove, that again, that is a true reflex. You're at the level of so it's not necessarily your brain. Your brain will recognize the fact that you're getting burned afterwards for sure. But what we're seeing in terms of the withdrawal reflex or the withdrawal from a hot stimulus reflex is that, again, it's very local and happening without the brain giving any input. So for example, I just tilt my screen down here. So if I touch a hot plate, the senses are working at my fingertips. They're sending a signal to my spinal cord, which is then sending a response without going to my brain right away, directly back to my muscles, telling me to pull my hand away. So again, it's a local response that the brain doesn't have time to control over. And yes, I have this last question here. Reflexes. So do reflexes work with your nerves? They absolutely work with your nerves. So what we're seeing on this picture right here, so this blue color, red color, and I think it's purple or navy blue, those are all nerves. So you're gonna have a nerve that originates in your muscle that goes to the spinal cord as one whole nerve, connects to a different nerve in the spinal cord that goes all the way back to your muscles. So there's no brain involvement, but there is definitely a nerve involvement. But that was a really deep dive into reflexes. So awesome. And these are great questions. I'm really enjoying them. We're going to move on though now to making muscles, which is the second exercise we're going to be going through today. So my question to people in the audience is that who here has exercised before, and does anybody know why exercise is important? Helps you lose weight. Okay, that's the first response that we had here. To stay healthy, awesome. Yeah, perfect. So those are two good first responses that we can kind of use. To stay active, to help keep muscles strong, awesome. These are the other responses that I'm seeing. So these are all great. And I think they're all right in some form. So I think the predominant reason why humans exercise and why we should be exercising is that it helps our body, like we're using our body in a more difficult state than is normally required of it, if that makes sense. So that when we put ourselves through exercise, and we'll talk more about this on these upcoming slides, we're putting our body and making our bodies work harder than it normally has to do. And our bodies are cool and are really cool in the fact that when we stress them and we put them into states that they don't really like, right? It's not really fun when exercise is most difficult. But by putting our body into that state of uncomfortableness where we're really stressing it, we're demanding a lot from it, our body then responds when we stop doing the exercise or in the recovery period by building back up stronger. And this has really great implications for all sorts of life. But we'll start talking about those right now. But awesome, thank you for those inputs. So if we go back again kind of to this, this evolutionary history of why exercise might be important. In the early days, right, if we go all the way back to the caveman days, humans weren't able to hit the gym like we can today, right? Most people today can work out in gyms, we can work out at home, we have exercise equipment that we use to help us work out. Back in the day, thousands and thousands of years ago, early humans didn't have these really cool exercise machines to work out on. Instead, the reason why they had to exercise was usually actually for a purpose. Most of their ability to exercise dictated their ability to survive. They had to chase down, they had to farm, had to chase down animals in terms of hunting, and this was very taxing on their bodies in a physical way. But the only way kind of that they realized that they can get better at these things is by continually doing it. And by waking up day after day, by staying on their feet, running to go chase these animals, to have successful hunts, they're building their bodies back up stronger. And over time, they were able to become much more fit individuals that can be more successful in their hunting abilities and in their ability to survive back then. But I guess, again, my question for everybody here is, actually, we'll just move on to the next one. Okay, so this is why muscles were important and really why human beings needed muscles in the first place, right? We didn't, it's not necessarily just to look good in the mirror, that really we needed all the muscles and we needed these muscles to be strong. So the fact that we could hunt and farm enough to be able to provide for ourselves and also for our family members. So there are two broad types of exercise. When we talk about exercise, there are two big types. There's something known as aerobic exercise, and there's something known as resistance exercise. And these are two broad types. When we think of aerobic exercise, we can think of things that get our heart rate up, where it's very difficult, we're panting, we find throughout the activity. And this could be like a game of tag, for example. It could be swimming in a swimming class, be going on a walk, going on a run, anything that elevates our heart rate for an extended period of time. And that really requires us to breathe heavily and breathe in high amounts of oxygen. That's going to be aerobic exercise. And we can just see on the picture here, kind of like it looks like either a dance class or an aerobics class where people are moving in ways that, again, elevate their heart rate. Whereas when we look at resistance training, this tends to be a little bit more focused. It tends to be more muscle specific, so area of the body specific than aerobic exercise does. And really its job is more so, it's working specific muscles to their max. So we're really putting either a heavy load or asking the muscle to work for a long period of time. But it's a little bit more muscle targeted. Our heart rate doesn't get up quite as high. We don't feel quite out of breath as we do with aerobic exercise. And again, it's more muscle specific. And the cool thing about these different types of exercise is that they offer different benefits. So when we look at aerobic exercise, really the big benefits come from the fact that it's good for our cardiovascular system. excuse me. It's good for our cardiovascular system, so our heart and lung health. It's very healthy for those. It actually helps reduce the amount of plaque buildup. And one of the things that happens as humans get older and we are not able to exercise as much is that we can have this accumulating amount of plaque. If we think about it, it's like think of like an old piece of gum that can just get clogged and then it can stick into our arteries and veins and cause blockages. But doing aerobic exercise helps to block against that and to fight against that. Aerobic exercise is also very good for our immune health and immune system that fights off viruses and bacteria. It's very good for our mental health and it helps improve mood. And it's also very good for sleep. By tiring ourselves out with aerobic exercise, it really helps people sleep longer and also more deeply as well. Whereas when we look at resistance exercise, on the other hand, the key benefits from resistance exercise come from the fact that it's very good for our skeletal health and our skeleton, right? So if we think about human beings, without our skeleton, we would be a sludge, like a pile of sludge. We wouldn't be much. But our skeleton helps give us frame. And as we get older, one of the key things that ends up happening is that our bones become less dense, they become less strong. But by utilizing resistance exercise, doing those specific movements helps strengthen our bones and strengthen our skeleton as a whole. Resistance exercise has also been shown to be very beneficial for completing activities of daily living. So whether or not it's pushing a cart at the store or carrying in the groceries from the car or reaching something on a high shelf. By doing resistance exercises, people have been shown to maintain their ability to do these different activities that we all love doing and they'll need to do for a much longer period of time. Resistance exercise has been shown to reduce our risk of falling and also risk of being injured from when we fall. And again, like aerobic exercise has shown to be very beneficial for mental health and maintaining a good mood, as well as being very beneficial for sleep as well. So the next thing we're going to talk about today is the types of muscle contractions. And this is something that until university, I didn't really realize there was a difference in the types of muscle contractions that we can then do. So if we think about it, there are three big types of muscle contractions. And I'm going to get my water bottle to mimic my weight. And we can all do this exercise at home as well if we want to kind of feel how these types of muscle contractions are different. So probably the most common or most known type of muscle contraction, something known as a concentric muscle contraction, right? So we look at all the videos of people in the gym or at different movies of people working out, right? It's a bicep curl is the key exercise that people see, right? People are curling biceps, curling heavy weight to get these big arms. But what the movement of actually bringing, and I apologize for the blurriness, but the movement of bringing the weight from my arm when it's out here all the way to my body, that is something known as a concentric muscle contraction. And it's called concentric because the muscle itself, which is my bicep in this case, is shortening as I'm working and as I'm having the muscle contraction going. So again, the muscle shortens as I contract. That's a concentric muscle contraction. Another type of muscle contraction that's a little bit less known, but still predominantly known, is something known as an isometric muscle contraction. And this is where the muscle length doesn't change as I'm contracting it. So example would be if I had a really heavy weight here and I just couldn't bring it in and it was just kind of stuck out here, right? My muscle is working really, really, really hard, but it's not shortening at all. It's contracting really, really, really hard, but it's not changing length. And that's just because, again, the weight is so heavy that I can't move it. Another example of an isometric contraction would be doing a plank, for example, where if we, again, have seen videos of people working out before, people are going to be on the ground if it was in front of me, and they're just holding this position. They're tensing up all the different muscles in their body, but they're not changing length. And that's called, again, an isometric muscle contraction. Now, probably the one muscle contraction type that most people are least familiar with is something known as an eccentric muscle contraction. And in an eccentric muscle contraction, the muscle actually lengthens as I'm contracting it. And this happens with very, very heavy weights. So if I was to put a very, very heavy weight in my arm right when it's at the top here, that it's so heavy that I just can't control it and it's still driving my arm downwards, my muscle's working really, really, really hard, but it's also lengthening at the same time. And this action of the muscle contracting but lengthening at the same time is known as an eccentric muscle contraction. So all that being said, kind of why do we care about the different types of muscle contractions? Well, it's important to care because we actually get different benefits from doing each type. So for people that are doing most sport-based movements or sport-based activities, where they're working out in ways that are very similar to how they perform in a game. So say they're running they're running sprints, or they're doing different footwork. If you're a football player, for example, they're going to be wanting to do concentric muscle contractions because it's going to be it mimics as close to the real game life as possible. But if we're looking to actually maximally work out our muscle, like some power lifters are, or some bodybuilders that just care about big muscles, they actually will use eccentric muscle contractions more. So again, a concentric is when it shortens, eccentric is when it lengthens, and most bodybuilders and powerlifters like eccentric movements more than concentric, simply due to the fact that you can put more weight on the muscle, you can break the muscle down more, then it also rebuilds back bigger when you're done building it. So that is, again, just why the different types of muscle contractions actually have an influence on types of training that you'll do. Where if you want if you want to do the most damage to your muscles so that it grows back the biggest, you'll want to do some eccentric contractions. Whereas if you just care about having that sport specific or functional training, that's really going to come from having the concentric muscle contractions. So the kind of next point here is, how do muscles grow? And there's two key principles that really utilize how muscles grow. There's something known as the FIT principle, so F-I-T-T. And with this one, we're seeing that it's frequency, intensity, type, and time. Those are really the biggest things that dictate how these muscles are growing. If we then think about the key principle, though, as we start training more and more and more, it's something known as progressive overload. So again, then the key kind of thing to think about this one is that we want to always keep working our muscle more and more, right? So if I work out, for example, with a 10-pound weight this week, and I do all my working out with a 10-pound weight, the next week I want to be able to bump that weight up maybe to 12 pounds or 15 pounds, so that I'm always working my muscle more and more, so that it always can keep going back bigger and bigger. If I just use the same weight if I use the same weight for the same amount of time always, my muscle's never going to grow, because you need to have these principles followed, as well as the fact that you're progressively stressing the muscle more and more and more. And one final point I want to make about muscle growth in general is that muscles don't grow in number. Some things, when they get bigger, for example, our bodies, for example, we have more and more cells, but it's not the case when muscles grow. With muscle cells, we actually have a very strict amount of number of muscle cells per each human body. But how we get bigger muscles is that we break them down, and that these individual muscle fibers tend to actually increase in size. And that's how we get bigger muscles. We're not getting more muscle cells, we're just making the cells that we have larger. So does anybody have any questions? And I just want to make sure I'm on track for time. Am I supposed to be done at 11:40, or do I have 10 more minutes? I just want to make sure.
You have 10 more minutes.
Okay, perfect. Yeah, because we have another exercise we can go through then. Awesome. But does anybody have any questions on making muscles? Nope. Okay. So let's get moving into our last exercise then today, which is magnificent microscopes. So before we dive into some of the microscope images that we're going to be talking about today, I need your guys' help in terms of naming the organs that are going to pop up on the screen. If people can name the organ and also state its big function in the body, that would be great. So in your responses here, the first one I think we're going to be on the ball with. So does anybody know what this organ is and what its key function is in the human body? This guy right here. Heart pumps blood. Amazing. Yep, that's exactly right. How about this one right here? Anybody know? Okay, awesome. I saw brain. I see brain in the chat. And what does the brain do for our bodies? in a couple words? Sending signals, awesome. Yeah, we'll go with that for now. But our brain is able to controls the body. I'm also seeing a bunch of other responses here. Awesome. Movements, it's the control center. Awesome. Yeah, it's that big control center that we have in our body that dictates all kinds of different things. Awesome. How about this one? This one's a little bit tougher. If we're looking on the right-hand side here. Which organ is this, and what is its key function in the body? Ooh, awesome, somebody got it. So yep, I'm seeing a bunch of responses now. The liver, which is great, and then it filters bad stuff, cleans blood, makes bile, stores sugar. Oh, who said that one? That's almost all the functions of the liver. Awesome. Yeah, so the liver. This is what we're seeing on this image here is the liver. It's that's great responses, everybody. And really, its job is to filter the blood, clean the blood. It's actually a big storage depot for different energy sources, whether it's fat or carbohydrates. And yeah, it's involved in processing our nutritional intake as well to make sure we have enough energy. Awesome. How about this one right here? This bean-shaped structure, shaped structure. Kidney, awesome, yep. And can anybody tell me kind of what the major function of the kidney is? Produces urine, awesome, yep. Filters blood, regulates electrolytes, awesome. Yes, these are all great responses. Yes, so these are our kidneys. They're going to be, again, those kind of bean-shaped structures we have in the back of our bodies. And their big responsibility is filtering the blood in a similar kind of way that the liver does, but really it's going to filter the blood and produce our urine that can then be excreted from the body. Awesome. So we got 2 more left. This one right in the middle here. What are we thinking? Awesome. Yep, so I see stomach for digestion of food. Perfect. Yeah, so the stomach through both mechanical digestion, so muscle contractions, as well as chemical digestion, which is its responsibility for producing certain chemicals. It's going to break down our food so they can be absorbed by a body. Awesome. And finally, this last set of organs right here. Does anybody know what structure this is? And what its function is? Awesome. I've seen a couple. Okay, yeah, lungs I'm seeing in the chat. Awesome, and for breathing, exactly. So we're gonna take air in through our mouth. It'll go all the way down this tube, which is known as the trachea, into the lungs, and the oxygen can be inputted into the blood, and carbon dioxide can be removed from the blood at this point. Perfect. Thank you, everybody, for responding. That was great. So these are the kind of big organs that we have in our body, and we just went over the kind of key functions for each one. But now the next part of our activities that we're actually going to be looking at certain microscope images and then trying to guess that organ from the microscope images. So I'm going to be giving hints out because this is going to get a little bit difficult, but I'm interested to see what we can come up with. So the 2 tools that we have to go about analyzing these types of tissues that we're looking at, we have a generic microscope, and we also have something known as an electron microscope, which is a very high-tech, very expensive microscope that produces very, very high-quality images. So using images that are taken from these 2 research tools, we're going to try and guess which organ they belong to, and we'll be reminded of the organ's key function as well. So first up in guessing that organ, these are the images taken from a traditional microscope, and again, we're trying to guess which organ these are. This will be the only organ that wasn't discussed earlier on that last slide we just went over. And again, if people have guesses, please feel free to throw their answers in the Q&A. Intestine, okay, very good guess, okay. The key hint for this one, and okay, that's a very good guess too. I'll show you the electron microscope image. So again, this was traditional microscope. So this guy right here, this was the electron microscope. I'll keep waiting for a couple more guesses. Okay, everybody's gotten it. You guys are awesome, on the ball. Yep, so this is actually the skin. So we can see here, these are 2 different images taken. This was more of a, this is an internal structure of the skin, actually, for what the inside of our body would look like. And this is what it's gonna look on the outside. And then this is, again, the electron microscope of the top layer of our skin on the outside of our body. And yeah, great guesses there. And the kind of the key thing I wanted to just highlight with this image is that we can see something known as keratin on the top of this layer. And with this keratin, it's actually non-living parts of our skull. So the non-living parts of our skin. So the top layer of our skin right on the top is actually not living cells, but productions of cells known as proteins that line the top and actually make our skins somewhat waterproof. Somewhat. We can still get water coming in though in other areas. Okay, next up on Guess That Organ. We have this image that was produced by a microscope, the traditional microscope, and this image that was produced by an electron microscope. What are we thinking here? All right, I got one person saying the lungs. Okay. What else are people thinking? Okay, and somebody says the intestines. Interesting. Any other guesses? Brain, it's also a good guess. Interesting. So the cool thing that we're seeing at this image is it's actually in the digestive system, in the GI tract. Intestines are a good guess, but it's not quite what we're looking for. This is actually a picture of the stomach. And what we can see here is that this was like looking more of a top down, whereas this is a cross section of the stomach. So we can see here that these little holes or pits are what we're seeing on this slide right here. And in these little pits in our stomach, which is one of the things that makes it unique as an organ, is that it can produce something known as hydrochloric acid. And this hydrochloric acid is going to be really important for breaking down food when we ingest it so that it can be absorbed by our body. But yes, awesome. Thank you for your suggestions there. Or for your inputs there. Okay, the next image. This is the image taken from a traditional microscope, and this is what we're looking at from a electron microscope image. This again is going to be related to the digestive system, but not kind of something known as a traditional GI tract organ. Anybody have any guesses here? We have 2 minutes left. I'm aware of the time, so we'll keep moving through it here. Okay, somebody's got it. So we had kidneys, but then the second guess here was liver, and that's exactly right. So we can see here, the liver is a very, very dense organ. So if anybody takes anatomy later on in life or is taking it right now, one of the things you'll notice that the liver is very, very heavy and it's very like it's rockish when you touch it. And this can be seen or corroborated by the fact that when we look at this microscope image, everything is densely packed together. And it's just because of how important of an organ it is that it has to be densely packed in order to do all of its different functions. All right, I have 2 more images here, but we'll go through them quickly. So this last couple images is actually a 2-for-1. So they're very related structures, but they're 2 separate organs actually. So what do we think we're looking at on the left-hand side here and on the right-hand side here? No guesses? Muscles, awesome. Whoever got that is perfect. It was right on the ball. So we're actually looking at 2 different types of muscle, but they are muscles. We have skeletal muscle on the right here, and we have our heart muscle on the left-hand side here. And the cool thing is that they look very different under a microscope, right? There's a different organization that goes on with our skeletal muscle versus our heart muscle. And finally, the last organ that we're going to talk about today, if anybody take a guess of this. This is the traditional microscope image, and this is the electron microscope image. Any idea what organ we're looking at right here? Oh, the lung's a good guess. Interesting. Any other suggestions though? Thigh, kidney. We're actually looking at. Okay, somebody's got it. There we go. We're actually looking at the brain here. So it looks weird, right? Like it didn't appear to me that this is what it looks like underneath a microscope. But this is definitely the brain. And we can see here on the electron microscope image, just showing the complexity of the different neurons and how they connect to each other in the brain. But with that, thank you everybody for their participation today. It's actually worked out a lot better than I thought it was going to, so amazing. And are there any final questions before we move on? But I also don't want to take up more time because I know we're right at the end here. So thank you everybody for your attention and your time today.
Thank you so much, Riley. That was a great presentation and I learned a lot. Unfortunately, we don't have any time for questions.
Okay, no worries.
But thank you again for your presentation. That was great. Okay, and so we will now have a very short activity from Science Chase, special activity number 1. And as a reminder, if you have any questions for our speakers, please post it in the Zoom chat and we will answer them if there is time. Science Chase, please take it away. So everyone, just if you wouldn't mind holding on with us while we get sorted here. Okay, so please join our Kahoot game. You can go to www.kahoot.it and insert this game pin to join. You have 20 seconds left to answer our first question. Moving on. Get your answers in. Looks like most of us got that one right. Nicely done. Oh, and WN is in the lead. Looked like that was a tough one for everyone. Galileo's invention was the thermometer. Nicely done, everyone. Most of us got that one as well. Looks like our leaderboard is getting closer and closer. And the correct answer was nitrogen for the most abundant. Ten more seconds. Perfect. The scientific term for sprouting is germination. And we have a new leader at the top of our scoreboard. Nicely done. That was a great question. Alexander Graham Bell discovered the telephone. Looks like Friendly Urchin 33 is still at the top of our scoreboard. Just a few more questions to go. Ten more seconds, get those answers in. Nice thing around it. This has the male give birth. Great job. Last two final questions and a little fun fact for you. Did you know that an ostrich's eyes are bigger than its brain? One more question to go. Congratulations to our third place junior chinchilla, our second place finisher Zed, and our first place finisher Friendly Urchin 33. Thank you guys for participating in our Kahoot. Please return at 12:10 and we'll go on break now. Okay, welcome back, everybody. We will now have Biomedical Engineering joining us with their activity, Biomedical Engineering at U of T. As a reminder, if you have any questions for our speakers, please post them in the Zoom chat and we will answer them if there is time. Please take it away.
Cool, thank you for the introduction. So I'll just pull up my slides here. Can you see the screen okay?
I can't see it at the moment.
Okay, just give me 1 second. How about now?
Perfect.
Okay, sweet. So good afternoon, everyone. Welcome to the presentation by Biomedical Engineering. My name is Jamie. I'm a PhD student here, and I'm with my colleagues Zara, Wayne, Ayo, Nafisa, Zach, and Carter. Today, we're going to talk to you about biomedical engineering, which is where we use engineering skills to solve problems in biology and medicine. And so one aspect of biomedical engineering is using nanotechnology to, diagnose diseases or treat them. Well, how small is nano? A nanoparticle is about 4 nanometers in diameter, and that's actually 1,000,000 times smaller than an ant, which is around 4 millimeters long. Well, how small is an ant compared to the NYC Central Park? That's another 1,000,000 times difference, right? So you can imagine how small the nanoscale really is. So why should we care about nano? Well, the reason is because your body is made up of organs, which are made up of even smaller units called the cells. And these cells are built with, things like DNA or proteins. And then these DNA and proteins are actually on the size of nano. And that's why when we use nanotechnology, we can directly interact with these building blocks of life. And that's why we can achieve a lot of functions that we want to do.
Hi. There are also a lot of different things that we can make nano-sized. We can make gold particles nano-sized. We can make fat particles nano-sized. We can even make some metals nano-sized. I have an example here of, okay, let's bring it a little closer to you guys. So these are gold particles. So these are nano-sized gold, which is pretty cool. We also have these iron oxide particles that have been nano-sized. When we nano-size iron oxide, we make them very magnetic. So here we have the particles. Here I have a magnet. So if I put a magnet underneath, we should see them become clear because all the iron oxide particles are being attracted to the magnet. There we go. And unfortunately, I don't have an example, but we also have these things called quantum dots, which are like metals that we've made into nano size. And when we do that, we can make them turn into different colors. And so that's the picture we see at the bottom.
All right, so as we've just learned, nanoparticles have lots of interesting and cool properties. And one of the things that they're really useful for is detecting diseases. So when you're sick and you have a disease, what we can do is we can take a little bit of your saliva or a little bit of your blood, and then we can add some nanoparticles to it. After we add nanoparticles to it, if you have a disease, the nanoparticles can change color. And then, if it changes to purple, then you have a disease. Or if you don't have a disease, the nanoparticles stay separate and they don't change color. And then that's how we know that you don't have a disease. So nanoparticles are really useful because they're a really quick way for us to know whether you're sick or not. And they're actually used in the COVID tests that you've all been testing and using.
Hello, everyone. So you're probably wondering, what is cancer? Well, cancer is a disease where something in one of your healthy cells goes wrong, and they start replicating like crazy. So these cells that are growing uncontrollably are called cancer cells. So in this left panel over here, what you can see is that there's one bad or cancerous cell, but because they rapidly take over all these healthy cells, shown on the right panel, you can see that the body starts getting sick and the healthy cells will start dying. So now you're probably wondering, well, what can we do to treat cancer?
The three most conventional methods of treatment are surgery, where we have to open you up. The other one is radiation, where they have to emit harsh waves right at you, and chemotherapy, where they have to stick harsh chemicals through your body. And so although these methods are generally effective, they are invasive and they kill your healthy cells while trying to kill your bad or cancerous cells.
Well, this is where nanoparticles come in, or nanomedicine. Nanoparticles can carry a bunch of different items on top of them, which allow them to have specific functions. For example, we can put drugs onto the surface of the nanoparticle to help cure a disease. We also have the core, which hold different cargoes or different items that can be used as a way to deliver a specific drug to your cancer tumor. Or we also have dyes, which are used to track the way the nanoparticle travels through the body. Like we can see on the panel to the lower left, where we have different colored nanoparticles being imaged as well. We can also put antibodies onto them to recognize a target. And this can be used to recognize different tiny molecules that can be found on the tumor, on the cells of the cancer cell. And with that, we also have these drug molecules, antibodies, and nanoparticles can all be injected made into a nanomedicine formulation that can be used to deliver to a cancer patient. Example, the lung cancer patient, and then this will be used to treat the tumor.
The more recent examples of us using nanoparticles to treat diseases is the COVID vaccines that we have. In the news, we often hear as a mRNA vaccines, but mRNA vaccine is the mRNA is actually the cargoes that we deliver to the bodies using this fat nanoparticle. And when this nanoparticle gets into the body, our cell actually has the machinery to use the mRNA to produce our vaccines and allow us to be immune to the COVID virus that's circulating in the air. So here we have a pop quiz. The first question is, how small is a nanoparticle compared to an ant?
So feel free to put in the answer in the chat box if possible and see if you get it right.
Yeah. And second question is, how can we use nanoparticles to detect diseases? And 3 is, how do you target nanoparticle to cancer?
I'll give them a minute here to answer those questions, and I'll let you guys know if I have any responses for you. So we have a few answers. Are you able to see them in the Q&A section?
Yeah.
Perfect.
The correct answer is the nanoparticle is a million times smaller than the ant. So the way we detect the diseases using gold nanoparticle is that it changes the color. And to target the cancer using nanoparticle, we can put antibodies onto the nanoparticles to target the cancers. So I think people.
Okay. Yeah, so I'm gonna switch gears a little bit. So I'm going to talk about tissue engineering and how we can use polymers to enable regeneration of different parts of the body. So what is a polymer? Polymers are large molecules made up of really small building blocks, which are called monomers, and polymers are everywhere. So they make up jello, which you can eat, and they also make up the components of fibers like nylon, which are part of the jackets that you might wear or the snow pants that you might have at home. So polymers are really useful materials and they happen all over the place. However, they can also be used in medicine and in tissue engineering. So gels, like Jell-O, are made up of polymers, and those gels, which are made up of those polymers, can be loaded with medicines, and those medicines can either be drugs or they can be cells. And we can use those gels that we make with those polymers to treat different diseases like spinal cord injuries or stroke, or even blindness, by loading it with different kinds of drugs. And one gel that we use a lot for tissue engineering is an alginate gel. So alginate is a naturally occurring polymer that you can extract from seaweed, and we use it all the time in the lab to culture cells and to treat different diseases. And the way that alginate works is that we get this polymer and it's got a negative charge. And when we add it to a solution which is composed of something that has a positive charge, in this case calcium, it'll form a gel. And if we add it to something like water, which doesn't have charged particles in it, it won't form a gel at all, which is less useful for us. So I'm going to show you what I mean. So can you see the table?
Yes, we can.
Okay, great. So what I have here, an alginate solution, and I've dyed it with food coloring and glitter. And these can be representative of small molecule drugs that we can load into our polymer solution. And the glitter can represent the cells that we might also encapsulate into the gels that we might want to form. So here is some of the solution. And so I have on the left a calcium chloride solution.
Sorry, Jamie, would you mind just speaking a little bit louder?
Oh,
Yes.
Oh, perfect. We can hear you better now.
Yeah, so on the left, we have a calcium chloride solution. And what I'm doing is I'm adding this alginate to it. And you can see that it's making what appears to be a gel. But when I add it to water, it doesn't really form a gel at all. It just forms like a liquid solution. Which is less useful because we want to use our gel to basically hold our cells and all of our drugs together like a glue. So pull out some of this gel here. You can see it forms this like big boogery type structure. And this is really useful for applications for stroke and treating blindness and all kinds of tissue regenerative applications that we might want to use in the clinic. So it's a really fun thing to play with, but it's also very useful for treating diseases. And you can usually buy these different solutions at like health food stores. So if you want to try this demo at home, all you need is a little bit of Jell-O and some calcium, and you're off to the races.
Okay. So that concludes our presentation from the Biomedical Engineering Department. Today we've learned that biomedical engineering is the practice of using engineering to solve problems in biology and medicine. And different ways to do this can include using nanomedicine, nanoparticles to diagnose and treat diseases, or we can use tissue engineering skills of making different polymer gels to load drugs and inject them into the body to also deliver drugs and treat diseases. So thank you for coming today, and hope you have a very, very nice rest of the weekend and enjoy the rest of the sessions.
Thank you guys. That was fantastic. I especially loved the little alginate gel demo. It was quite nice. We have a few questions from the audience.
Okay,
Our
perfect.
first question is it safe for the body?
The gels?
Yes.
Nanoparticles. Yeah, so the gels are made up of naturally occurring substances, and they can usually be degraded by the cells that are in your body. So while we have this gel for a short period of time, usually the cells that are naturally occurring inside of you will just degrade it over time, and it will be flushed out of you as anything else might.
Thank you. And perhaps this question might apply to many of you, but is there a specific nanoparticle that you find very interesting and why?
I find quantum dots pretty interesting. They're used in many applications, from medical to entertainment industry. They're used in our TVs, and we also use them to track various track how organisms or molecules flow within the body, and also used to detect diseases. So many functions for one tiny particle. Yeah. Any other questions?
Were there any other different responses?
Oh, yeah.
Hi. So I find gold nanoparticles really cool, just because they can be made into a wide variety of shapes and sizes, and you can put a bunch of different things on them. You can put colors, so like dyes, and so this makes them very useful for diagnosing a certain disease. So for example, if you want to see whether or not you have a cancer and you want to be able to use some sort of imaging technique to see them, you would just inject a bunch of nanoparticles that are gold, that have dye on them, and then you can inject them in, and then you can use x-rays, or not x-rays, sorry. You can use different imaging techniques to be able to see them. And yeah, it's really cool. It's like a bunch of different colors and shapes. Yeah, it's really cool. I like nanoparticles.
Awesome, thank you. I like the different colors. We have another question from the audience. Why should we use this gel over bacteriophages?
Oh, so bacteriophages are a type of virus that infects bacteria. This gel that we might use for tissue engineering applications is very different, because basically what we would use it for is we take these polymer chains that make up this gel, and they form sort of a scaffold or things that cells and drugs can latch onto. So the reason why we might want to use a gel is because if we want to deliver a medicine to a particular part of the body, or we want to fix just a small defect in like a bone, or we want to fix a defect in the brain, we would want to take our gel and we would want to locally administer it to that point of injury. So it's really useful for basically providing the structure for the cells that we might want to deliver, as well as enabling like the localized delivery of the drugs that we might also want to encapsulate into our gel. But bacteriophages are also very useful for many other applications, but it's just a slightly different thing.
Thank you. That was a lot of really good information, so I really appreciate that. We have a few more questions if you guys are okay. We also have, why did you guys go into nanoscience and biomed?
So for me, so I actually studied chemical engineering before. So in that I studied how to design factories, design oil rigs, design oil pipelines. But then when I actually so I got into labs that does biomedical engineering, and what my project was to use bacteriophages actually to put onto nanomaterials, nanofilm, and to detect bacteria in spoiled food. And that was a really interesting project. And that's how I switched from learning how to design factories into how to make nanoparticles and how to treat cancers.
Thank you. That's very interesting. Did anyone have another reason that they would like to share?
I like to share. So I went to nanoscience because when I was a kid, I opened up a book and I saw a picture of these little viruses, so these nano-sized little particles going through, and I thought, how cool it'd be if we can build stuff like that and build tiny little nanomachines. So, that was basically the inspiration. Now I get to do it, and it's a lot of fun to just build little particles and see where they go and how they behave in the body.
Awesome. I like it. It sounds like you're very passionate about it too, which is great. I have another question here. What is tissue engineering?
Yeah, so that's a great question. So tissue engineering is trying to basically regenerate different tissues in the body after they've suffered an acute or a chronic injury. So what we're aiming to do with tissue engineering is to basically repair different things that might have been damaged after an accident or because of a disease. So in the context of spinal cord injury in tissue engineering, what we're trying to do is we're trying to take scaffolds and drugs and cells and using a combination of those three things in order to help regenerate the nerves that might have been damaged because of some sort of accident, and enabling them to repair themselves because the body isn't capable to regenerate certain tissues. So what we're trying to do is encourage it and overcome the obstacles that might have be disabling it from actually repairing itself.
Thank you. That's a great answer, and it sounds like very important work. We have another question here from the audience. Aren't plastics polymers, and isn't that bad?
Yeah, so there's lots of different types of polymers. Plastics are polymers. So you can have polymers that are made up of natural materials like alginate, which are able to be degraded by proteins like enzymes, which are secreted by different cells in the body. So the reason why a plastic might be more harmful over an alginate polymer gel that we might introduce to the body is the fact that the alginate is readily degraded by the cells that are present in your body. However, the plastic isn't necessarily degradable by the cells in your body. So what might happen is if you take plastics and put it in your body, you'll engage an immune response where all of your cells will start attacking the polymer and trying to cause all kinds of inflammation, which can lead to all kinds of damage in the area where you might have put the plastic. But with the alginate, because it's naturally occurring and it's easily degradable, there's not this massive immune response. So the tissue won't be degraded by those attacking cells. It'll just be naturally sort of washed away over time. Yeah, so there is differences. It just matters what you're putting where and whether it's naturally occurring and actually can be degraded by the body.
That's great. Yeah, and just a quick follow-up question. I know you mentioned in your slide that seaweed was one of those natural sources. Are there any others?
Yeah, so we use all kinds of different naturally occurring polymers for tissue engineering. Another that we use quite frequently is collagen gels. And the way that we get that material is extracting it from the bones of animals. So cow bones are a really good source of collagen for tissue engineering applications. We also use methylcellulose, which is also another naturally occurring polymer. And we can actually extract that from bacteria like E. coli, which can produce it.
Fantastic. And I have a few more questions here from our attendees. Someone is asking, do you do any work with nanoparticle delivery of genetic therapies?
So I think Wayne, would you like to take this one?
Sure, I can take this one. So we actually do think a lot about how to deliver genetic therapies with nanoparticles, and that's because there's so many really beautiful technologies come out about how we can rewrite genetic codes and how to change gene expression in cells. But one of the problems is that they're all made outside of the body. So a big problem is how do we get these technologies from outside the body into the body? And really what we need to do is be able to protect them from the body so they don't break down. And one of the great ways to do that is by pretty much putting them into nanoparticles. So that's very much an emerging field. And there is a lot of work going on regarding how to basically protect them and then how to take these technologies to a disease site so they work.
Sounds very cool and like, again, important work. Are there any other applications of nanoparticles outside of biology?
Yes, there is. So the TV screen that we are using are actually quantum dots inside them. Another way of using them is in factories where some reaction requires catalyst to actually start, and nanoparticle or nanoscale structures are very good catalysts to start those reactions.
Awesome, that's great. Any other ones that you guys want to mention, or was that?
So one really cool one that I was looking into is people are starting to use like different metal nanoparticles like iron oxides for within like water filtration devices. So for example, if your water in your community is contaminated with a certain type of metal, what you can do is you can start like building these filters where they're coated with different metallic nanoparticles or magnetic nanoparticles to start attracting these harmful metals from the water. And so hopefully they'll be better suited to drink after it goes to this device. But I found that really cool. I found that out like a couple weeks ago.
That sounds awesome. We were hoping to get a little bit more information about how you make things nano-sized.
So that's a really complicated question because there's lots of ways we can make things nano-sized and lots of different materials we can nano-sized. I'll give you a few examples. So for gold and other metals, we typically just grow them into nano-size. So you can kind of imagine you're growing a little crystal of some sort, right? So you start with a little bit of dissolved salt, and then it grows a little bit, and then we just stop the reaction when they're still nano-sized. The other example I could give is something like the fat particles that are used for vaccine delivery. So to make those things nano-sized, we typically use something called microfluidics. So we mix them with a little bit of water, and then we spin them really fast. And then because the fat particles or the fat molecules that stick together, they naturally form things that are nano-sized. So that's two examples.
Thank you. And I have one question here. Why is nanoscale important? And could we perhaps go to a different scale?
Yeah, so I can take this one. So as we mentioned in earlier presentation, nanosize is important because it is on the same scale as the building blocks of biology, right? So if you think about, again, your body, they're made up of these organs, and the organs are made up of cells. And these cells are about 100 times or 1,000 times larger than the nanoparticle. And they're made up of proteins or DNA that are actually around the size of nano, right? So if you have something that's you're trying to enter a house, let's say, right? You will want to go in as something like a person size, right? To go into the building. You wouldn't want to let's say use another like a train to like ram into the building, right? You cannot kind of get into the building that way, right? You want something that's small, that are on the size scale of these let's say the doors of the building, right? Person can walk in and deliver whatever therapy that you want to get into the building, right? And the building here is, again, this is a cell, right? So you want something that's very small and can kind of penetrate these biological barriers that the cells or the organs impose. And that's why nanocells is nanoscale is important.
Thank you. And our last question, I believe, is wondering about if you collaborate with industry in your work.
Yeah, so at U of T, and especially working in biomedical engineering, there's lots of opportunities to work with industrial collaborators, designing new and exciting therapies to treat different diseases and to improve overall human health. So there is a lot of collaboration with pharmaceutical companies, and there is a lot of entrepreneurship that happens within biomedical engineering at U of T with the different faculty members who are also working to commercialize parts of their research that they think would be well suited to the clinic and able to help as many people as possible.
That's great. It sounds like a good collaboration. We actually had a few more questions just come in. Are organelles on the same scale as nanoparticles?
No, organelles are not the same scale. They're slightly bigger.
Very cool. And one last one. I've heard about graphene in nanotechnology. Hopefully I pronounced that correctly. Can you explain why it is so special?
So I'll try to explain this one. I'm not super familiar, but graphene is made out of carbon, and basically you can think of graphene as like carbon atoms, but they're kind of built in a very organized way. And under those properties, when you have really organized carbon atoms, they have these special properties, right? I think they are very, very like electrically conductive, right? So then they can be used in materials that needs to be highly, highly conductive, right? As opposed to carbon that's very disorganized, let's say coal or, other things, right? So then, how these atoms are arranged on let's say nanoscale gives them these special properties that you can use in different technologies.
Thank you. And thank you guys so much again for your presentation and answering the swarm of questions we just threw at it. It was all very interesting. So just please join me in thanking this department one last time before we move on. Thank you guys.
Yeah, thank you for all the questions. They're really, really great questions, and we enjoyed spending this time with you all.
Thank you. Okay, we will now move on and have the Leslie Dan Faculty of Pharmacy and Pharmaceutical Sciences Graduate Student Association joining us with their activity about DNA extraction. As a reminder, if you have any questions for our speakers, please post them in the Zoom chat and we will answer them if there is time. Please take it away.
Thank you so much. I'll just start sharing. Okay, can everyone see the screen? Thanks. So hi, everyone. So we're basically a part of the Leslie Dan Faculty of Pharmacy, and we'll be showing you a demo on how to extract DNA from strawberries. So first, I'd like to introduce all of my teammates. So Shanzay Chowdhury, she might be on the call. I'm Tiffany. This is Huyen, and this is Quinn, as well as Valerie. So everyone, I'd like to first acknowledge my entire team for putting this all together, and we'll get started. So with our short introductory presentation, we'll first explore a little bit about DNA and why it's so important for the pharmaceutical industry. So to start off with, what is DNA? So DNA stands for deoxyribonucleic acid, and it's a long molecule in the shape of a double helix that's made up of sugars and phosphates. So the spirals are connected by bases, that stretch between the spirals like rungs of a ladder. And DNA bases are adenine, thymine, guanine, as well as cytosine. And DNA essentially holds instructions for making all of our proteins, which are needed for our development and survival. So we can think of it like a recipe for our recipe book for our unique genetic codes. And this genetic code influences many of our traits, such as your eyes, your hair color, height, and even the size of your nose. So of the million of genetic building blocks that make us living things, only a handful are uniquely ours. And despite all of our differences on the outside, humans are actually 99.9% genetically similar to one another. And we also share DNA with other living things. So on this slide, I've listed 4 different living things we may share some DNA with. And do you want to guess how much DNA we share with these things? You could input it into the chat box. So you could guess how much DNA we share with chimpanzees, fruit flies, banana, and strawberries, which we'll go further into. So feel free to guess in the chat while we discuss.
Are you able to see the answers in the Q&A? If not, I can read them out to you.
I think.
Stop here.
So I think 99% for monkey. I think there's also some. And then let's see. Yeah, so 99.99% for banana, 89% for chimpanzees. How about for strawberries? What do you think? For fruits, how much do you think we share? %18 for strawberries. How about for fruit flies? How much do you think we have in common? %50, 60%? Any guesses? I think I see some fruit flies, hopefully 0. Okay, so let's see how many guesses are right if my slide is changing. Oh, I think it's going backwards. Okay, here we go. So we basically share 96% of our DNA with chimpanzees. So this is because humans and chimps are closely related. So we descend from a single ancestor of species that lived 6 or 7 million years ago. And as humans and chimps gradually evolve from a common ancestor, their DNA passes from generation to generation, and it changes too. And these evolutionary changes lead to differences between humans and chimps, especially in our appearance as well as our behavior. And the next three really surprised us as well. So we share 61% of our DNA with fruit flies and 60% of it with bananas and strawberries. So you might be thinking, how can we share so much of our DNA with an insect or even with fruits? So the relationship between fruit flies and human genes is so close that the sequence of newly discovered human genes, including disease genes, can be matched with equivalent genes in a fly. So this is one of the reasons why fruit flies are among the most studied insects. And as for bananas and strawberries, many of our what we call housekeeping genes that are necessary for basic cell function, such as for replicating our DNA, controlling our cell cycle, as well as helping cells divide, these are shared between many plants, including bananas and strawberries. So you can also let us know in the chat which ones you were most surprised about. And the ability to extract DNA is essential to studying the genetic causes of diseases for the development of, So it's essential for studying genetic causes of diseases for the development of diagnostics and drugs. And DNA extraction isolates DNA in a biological sample to separate the genetic material for the rest of the cell. And this is essential in pharmacogenetics, which is the study of the link between an individual's genetics and how they respond to certain drugs. So it's an integral part of the drug discovery process, and it aims to detect, monitor, as well as treat the molecular causes of diseases. And on the next slide, we'll explore some examples of how DNA can be used in drug discovery and why it's important in pharmaceutical sciences. So monoclonal antibodies are lab-produced molecules that act as substitute antibodies that could restore, enhance, or even mimic the immune system, how the immune system attacks individual cells. So access to DNA sequences allow researchers the ability to engineer structures and specificities, promoting the rapid generation of highly diverse libraries. And antibodies represent more than 80% of biopharmaceuticals, covering a wide range of disease areas, including oncology, immunology, and infectious diseases. And DNA technology also expands the possibilities for the development of improved or new biomolecular therapies. So these therapies allow DNA to be introduced into a patient to treat genetic disease. And on-demand access to DNA could also aid in the drug discovery process, particularly for addressing challenging targets. And lastly, DNA is required for the development of many vaccines, as the COVID pandemic has shown the speed of developing novel vaccines to cope with outbreaks and evolving variant strains is very essential. And DNA vaccines use part of the genes of a virus to help your immune system fight off the disease. These are just three examples of the many examples of how DNA can facilitate the drug discovery process and improve therapies and treatment for a variety of diseases. So this kind of concludes our introduction into DNA and why it's important in our field. And now we're going to jump into our presentation on how you could actually make your own extraction kits at home to extract DNA from strawberries. So here you can basically see the protocol that we'll be using and how you'll extract it. And we'll explain it more in the demo, but you'll be starting off with strawberries. What we want to do is we actually want to remove the leaves and the green part. It makes it easier for smashing, and you can't really, it's really hard to smush the leaves. So we're going to remove that. Afterwards, we're going to make what we call our DNA extraction liquid. So this is basically, you're mixing a detergent, salt, and water. So our detergent will just be soap. And we're going to mix it all into a cup, and this will be our extraction liquid. Afterwards, we're going to combine the extraction liquid with our strawberries, which we will actually crush into, you'll see it'll be like a kind of smushy, like it'll be very smushy in the bag. Once we combine both into, and we'll actually gently smash it a little bit more for another minute or so just to have the strawberries and the detergent mix. We're going to filter this. So you could use a coffee filter, or we'll show you, you can also use a strainer, which works just as well, and it also goes by a lot faster. We'll strain our mixture into, you could use a jar, we'll use a beaker in our case so it's easier to see. Once you strain it, we're going to pour rubbing alcohol. So this is isopropyl alcohol. We're going to pour an equal amount into the jar with your strawberry mixture. And what you'll see is that the DNA will start to separate from your strawberry mixture, and we'll actually be able to see it. So one of the nice things with strawberries is that it has a lot of DNA. So it has, I believe, 8 copies of your genome, whereas usually most organisms and cells only have 1 copy of your genome, which is what makes strawberries so great, especially for visualizing DNA. So I will just stop sharing my screen. And then if you could spotlight Quinn's. Is it spotlighting?
There we go. Should be okay now.
Perfect. So we'll move over to our setup. We need to. So what you'll see here, I've already measured out everything. Okay. Sorry. Okay. So basically what we'll need is you'll just use any kind of soap that you have at home. You can use, it'll be nice if it's clear soap, but we don't have clear soap. I was only able to get my hands on this, which is also okay. What you'll need is 20 mils of soap. It doesn't have to be exact.
About 1 to 10.
So this is 20 mils of soap. And this is 180 mils of water. And what we'll basically do is we'll first just mix in the soap and the water. So we'll pour that in, or actually I'll leave that up to Hogan. You'll also need some salt. So it doesn't matter if it's iodized or non-iodized salt. You'll need about a teaspoon of salt. You'll need a plastic bag where you'll actually go and smush the strawberries, a strainer, and that's about it. So I'll let Hogan take over.
Okay, add the salt already?
Yep.
Oh, so we need to add a little bit of salt.
So just a teaspoon of salt. It doesn't have to be exact either.
And now to get the DNA out, we have to make a strawberry smoothie first. So remove the leaves. You can use about 4 strawberries should give a good amount of DNA. Anybody like strawberry smoothies out there?
I do.
They are great. So now we have 4 strawberries, and now we're going to proceed to make strawberry smoothie. You have to make sure you get rid of all the air, so when you start smashing this thing, it won't pop right out of the bag. Smash strawberries are surprisingly tough. So this process helps a little bit release the DNA content, but we also need to add soap. And soap, because the DNA is in the cell nucleus, so there's a cell membrane and there's a cell nucleus, and we need to get that DNA out. And soap is perfect for that. The reaction of the soap with the cell membrane will just rip it apart basically. And it's actually very close to some of the chemicals we use in the lab to digest tissue samples to release the content. Like for example, we want like proteins or DNA inside a cell, and it's in a animal tissue. We also use similar detergent to extract those contents from the cells. So which makes you wonder, why do we even buy very expensive detergents to get things out when we need to use soap? Oh, so yeah, that's why you need to release a lot of air. Otherwise, it will pop right out of the bag. Okay, so you can see kind of like the strawberries are kind of dissolving already because of the soap. So now we're just gonna let it sit for a little bit. Okay, I think that might be good enough. Or do we need to wait a minute for this process?
Just want to make sure they're good and squished.
Yep. And we also add a little bit of salt to the detergent, and that's because we want the DNA to start humping. So DNA, because of the phosphate groups, it's actually negatively charged. So when you add a salt, which is a sodium chloride, and sodium, when it dissolves, it turns into sodium, which is a positive charge, and that will interact with the DNA and start clumping up the DNA. So that will make the process of collecting DNA a little bit easier. So they won't be single-stranded floating in your solution. There will be a clump. Okay, I think that might be good enough. Okay. Might be
You want to take this? Yep.
Oh, there's
Okay.
So
you want to pour? I
can move it.
Okay. Sounds good.
So
So we're just going to pour the strawberry mixture through the strainer, and you could use a coffee filter, but we found this was a little bit quicker. And it doesn't really matter which one you use, just whatever you have on hand. And there's going to be some strawberries clumping at the top. That's totally fine. It's okay if you didn't smash them all the way. You still should be able to see the DNA when we get to the end.
Yeah. Okay.
Yeah, and you can squish it down a little bit as well. Let me just get the rest out of this bag here. You're basically just trying to get all the juices into the beaker at the bottom.
Okay.
This is mostly just pulp at the top that you're collecting. And the stuff in the bottom is really what we care about. So you can do whatever you want with this strawberry goop at the top.
As you can see, a lot of it are still dripping down, but this should be good enough. Okay, I think that's fine. All right, we don't need that anymore.
Great. And then this is just some pre-chilled isopropyl alcohol. You can get this at whatever your local grocery store or anything like that. It's just pretty easy to get. And I'm gonna pour, so there's about 200 mils in here. I think I'm gonna pour another 200 mils in approximately. It doesn't have to be super exact. So just basically double the volume. So I'm just gonna pour about the same amount of alcohol in as there is liquid right now. So 1-to-1 ratio. And we'll just let it sit for a bit. And what you can see happening right now, that white kind of fibrous looking material, that's actually the DNA that's starting to clump. And when we give it a little bit of a stir, you'll be able to see it a little bit better. And it's this thick kind of gooey substance. And we can try and pull it out so you can see it a little bit better. Do you want to maybe hold it at the top too? Because you can kind of see these clumps forming. And it's this really gooey mixture here. And this is what the DNA actually looks like. And there's actually quite a lot for the amount of strawberries that we used. And it feels very squishy. And you can just put it on whatever you have around. It doesn't need to be a coffee filter. It feels a little bit slimy. There's actually quite a bit here. You can also use a spoon to scoop this out. I just am using whatever I had on hand. It doesn't really matter what you use. It should just like kind of clump together. And I'm not going to be able to get all of it out, but that's okay. And so what the alcohol actually does is it lets the DNA kind of precipitate out so that you can actually grab it out. Yeah, so you can see that nice little glob of goop. That's all DNA right here. It's actually quite a lot for the amount of strawberries that we used. Yeah, I'm probably not going to get all of this out. But then, yeah, so that's basically what it looks like. It's very squishy. And then if you let it dry for a couple days, this is what it ends up looking like. So a little bit different, but you can still see kind of the colors from the DNA that we had dropped onto there as well. Yeah, so the DNA is, you can see it's kind of fibrous and stringy. And you can actually touch it as well. Well, maybe not through Zoom, but you can see how it's kind of like stringy and has strands. What we'll do is we also have a pre-recorded video of a DNA extraction from a banana. So you can kind of see the difference in just how much of the DNA you could extract from, say, a strawberry versus another fruit. So if I could get the moderator to play the video, maybe.
Sure, yeah, we'll get right on that. Just a quick moment.
We are gonna do second demonstration to extract DNA from banana. And I got this small piece of the banana, and I am gonna put inside the big bag, and then make sure to seal well. And I am gonna mash the banana until all numb is gone. Make sure so that there is a little bit air. Make sure it's all on. You should get pudding flags shape after you mash very well. And then now I am done. I am gonna move the on this cup. Already the measured 15 milliliter water. I'm gonna pour inside. 1 teaspoon dish soap. Time is over. I'm gonna pour. Make sure the separation. Between 5 or 10 milliliter the juice. The here is we got the 10 milliliter. And then now I'm gonna pour this one inside the glasses. And this is my cold ethanol. I'm gonna slowly pour inside. Can you see the DNA, the branch one? Sorry. This is the RDNA. Thank you.
Okay, so you just saw a DNA extraction from a banana. So what you'll notice that's different between how we were doing it and how the video was, one thing is that we weren't actually using any gloves. So what's nice about this experiment is that everything is very safe. You could get it all from either the grocery store, or you might even already have it at home. So unless if you have cuts or something, then you could wear gloves because you don't want alcohol to kind of touch your cuts, that will burn. But everything else is completely safe. And what you'll notice is that, so strawberries, when you're doing a DNA extraction at home, you want to use something that is very easy for you to smush. So bananas and strawberries are great in that you could do it. You could also do it with like chicken or other like harder vegetables, but you'll probably have to use like a blender or something to be able to extract DNA from these kind of organisms. You can also try with a tomato or anything that's easy for you to smush and crush. The other thing as well, we've also tried this experiment with the rubbing alcohol that's not cold. It doesn't really have to be cold for it to work. This experiment is almost foolproof. You'll almost succeed every single time that you do it, which is nice. So I encourage you to also give it a try at home whenever you have the chance. And then we're also open to any questions that you have.
Thank you so much. That was fantastic. I love the demo. It was great, and the video as well.
And so first question. Oh, sorry.
Are you able to see the question?
Yeah, I just saw one. So does that mean we can extract our own DNA at home? So it might be hard for us to extract our own DNA since you can't really extract it from here. You'll need a much harsher detergent to actually break apart any DNA that you could get. But I probably wouldn't recommend doing it from getting your own DNA, but it is possible. So if you were to, I believe you know about Ancestry.com and like some other places where you just take, I believe, a swab of your saliva, you ship it off to the company, and then they actually come back and let you know kind of your history and ancestry, which is pretty nice. So you can actually extract DNA from saliva. You might need a lot more if you want to extract it at home. when you ship it off to a company, they have very fine materials that they use, as well as very sophisticated equipment to actually be to extract DNA from that small amount of saliva you send.
Fantastic, thank you. And I have a few more questions for you. So when we extracted our DNA, we pulled it out of that solution. What was in the solution that we left behind?
Yeah, so that's basically some of the pulp and debris from the strawberries, like the strawberry cells themselves, that pass through the strainer. So what you could do is you could also use a coffee filter, which also helps to strain it further. And you'll find that that solution is less clumpy. There's less, I guess, particles that pass through compared to a strainer if you were to use a coffee filter. So you could kind of see in that banana video, the solution was quite clear with a coffee filter.
Fantastic. And we have another few questions from our audience. How many DNAs does a strawberry have?
Yeah.
Sorry about that, we're back.
Some technical issues. So that's actually a great question. We don't actually know how much, unless one of my teammates.
There's 8, so strawberries are called octoploids, which means they have 8 copies of chromosomes, but I do not have the exact number of genes, but there's 8 copies of chromosomes in one cell of a strawberry. And yeah, that's a lot. And actually most plants and fish and amphibians have multiple copies of chromosomes, way more than humans. Humans only have diploids. So this brings us a point that the more complex an organism doesn't mean it has more DNA. So there's another question actually for you guys. There's a single cell organism called Paramecium. Do you know how many copies of chromosomes it has? Can you look at the chat to see if anyone answered it? How can you look at the chat for this one? There it is. I can't really see the chat here.
I think we have an answer.
Did it freeze?
Oh, I think it was frozen. I think.
Hello?
Hi, can you guys hear me?
Yep. Well, was it frozen already?
No. So we have someone in the Q&A who answered 3.
3 for the single cell organism. There's actually 50 copies of chromosomes in this single cell organism. So yeah, the more complex the organism doesn't mean there's more DNA in it.
Thank you. That was a very good question. We also have another one here. Are the materials you used in the demo similar to what you typically use in the lab with extraction? And do you have to use special kinds of chemicals?
That's a good question. I personally have not done DNA extraction in the lab. I don't know about either of you.
Yeah, so they do use different chemicals. So those you do want to use gloves, also to avoid any sort of contamination when you're doing an experiment. And you can actually purchase DNA extraction kits. There's a bunch that's actually available for us to use and purchase. Many companies have their own kind of mixture that they consider as a DNA extraction. Some are more efficient than others. But yeah, it's definitely different from what you use, but it's basically almost the same component. So you need some sort of detergent. You need something that could actually kind of precipitate out the DNA into your solution. And yeah.
Yeah, and these products are standardized. So to ensure when you do experiments, it'll be repeatable. If someone else do experiment and they use the same chemicals, they should theoretically get the same results.
That's a great comment. What do you think might happen if, say, you had 2 different chemicals? Do you think your results may be different?
Different chemicals?
I mean, as long as they're doing the same thing, like Tiffany mentioned, right? You need some type of detergent, something to precipitate the DNA out. The materials you're using shouldn't change the DNA in any way. All you're doing is separating it from the liquid. What it would change is what's left behind. So what's in the remaining liquid, that composition of mixture of things, that would change if you're using slightly different ingredients. but the DNA is the same. You're just taking it out. So as long as you're extracting that and you're pulling that out, the material shouldn't actually change it in any way.
Great, thank you. We have another question here. What does DNA do for you?
You want to answer? So DNA is the building block. It contains information of an organism, and you need DNA to make copies of yourself, just like a virus do.
Yeah, so you could think of it as what kind of gives you your own hair color, the color of your eyes, the shape of your nose, what your face looks like. All of that is dictated through your DNA. So your DNA is super important. It's found in every single cell in your body, maybe with the exception of red blood cells. That's a little different. But yeah, even other organisms, like fruit flies, strawberries, almost every living organism that you see will have their own DNA that basically dictates how they grow up, how they develop, what they look like.
There's also scientists who study the relationship between genes and behavior. So even like how our personalities change, how we view the world, and how we're different as individual people. There are researchers who actually study that and how our genes might influence that, and also how genes might lead to different diseases and stuff like that.
And it's super important in our field as well. There's a lot of researchers that you may have heard this kind of be tossed around called precision medicine. So what they do is within that field itself, they actually look at your genes, and then they'll actually kind of use that to be able to figure out what sort of treatment you should get if you have a certain disease, even like whether or not you're more prone to, say, getting cancer. So if you have a certain gene that kind of in your DNA that basically suggests that later on in life, you're more likely to get cancer than someone else who doesn't have that gene. So this is also a really important field that gets studied, especially in pharmaceutical sciences for the development of medicines, especially tailored to your specific person and your specific needs.
Thank you. And a follow-up question we had on that was, so we know genes affect behavior. Can it work the other way around?
That is an excellent question. So it's complicated, but basically there's this field called epigenetics, and it's how your environment actually influences your genes. So your experiences when you're a baby, your experiences as you're growing up, those can actually influence your genes. So it can, you're right, it can have kind of this back and forth relationship where your genes influence your own behavior, and also like your environment and what you experience throughout your lifetime will actually shape your genes. And sometimes those changes that happen can even be passed on through generations to your kids, for example.
Very cool. Do you guys work with DNA all the time?
So
not in my lab.
Yeah, not in my yeah, so pharmaceutical science is great in that our kind of like expertise and like our field itself is so diverse. So we don't actually work with DNA, but we work in other things. So I do some nanoparticle stuff. I believe Podian also does nanoparticle.
Oh, actually, my lab does do one of our projects, or one of our students working on a type of DNA called siRNA. And that's a whole different field. It basically uses another form of DNA, and that kind of affects the your gene expression with using this specific small sequence of DNA.
Yeah, and my lab actually does neuroscience. So we actually study the brain and how the brain works to learn and create memories, and then based on that we can develop new drugs.
Yeah, within pharmaceutical sciences, there's a lot of researchers who actually work with DNA, and also, like Hojin mentioned, another form of DNA, RNA, to actually develop certain medicines as well as certain therapies like immunotherapies to basically help treat a number of different diseases.
Very cool. And we have another question here that might be somewhat related. Do drugs interact with your DNA?
Yes, they do actually. Cancer drugs interact with DNA. That's how. So these drugs get inside the DNA of the cancer cells, and once they get inside, kind of block the ability of these cancer cells to replicate their DNA, and that's actually how many of these drugs work. They're called chemotherapeutics, and that's their mechanism of action. But it's kind of like a double-edged sword because this kind of drug will also affect your normal cells. So the reason why it affects cancer cell more than your regular cells is because cancer cells grow a lot faster than any normal cells in you. And that's basically ensure a little bit of specificity towards cancer cells.
Right, and not all drugs do, though. There's lots of drugs that work in many different ways. And even like the vaccine for COVID-19, that does not actually change your DNA at all. So there's lots of different interactions with drugs in your body. And some of those do involve DNA, but a lot of them don't. Yeah.
We did actually have a question about COVID detection. We had an attendee wondering whether this was the same extraction technique used for COVID detection.
I think it might be because when you give it'll be a similar technique because they give you a saliva and then they test the viral particles in your saliva. But I don't think it might be. It could so that your saliva will contain the virus and also any cells that are affected by the virus. And if you take those the viral DNA or DNA or is it RNA? Corona.
Yeah, so
I think it would be RNA, right? Corona. Yeah.
So basically, with like the test kits, even when you send your samples to do, I think you've heard of PCR testing. So they use very sophisticated equipment. And in terms of actually being able to detect your viral load, so you can imagine the viral load is very, very tiny. It's not like with the strawberry, how you saw a huge clump, a massive DNA. Basically, from your saliva, there's only a tiny amount of the virus. And you could think about it as basically, you don't really give a lot of your saliva for to like send off to test. So what they do is they need something they call as PCR, which actually helps to kind of amplify or increase the amount of the virus for them to actually be able to detect it. And this is all with very sophisticated machinery, much more sophisticated than how we were doing it with. And there's a whole lot of fine details that go into in terms of the material, the solutions, the chemicals that they use to be able to perform such extractions. And yeah, but almost, I wouldn't say same process, but very close. The difference is in terms of how they actually be able to amplify the amount of the virus for them to be able to a level where they could detect it.
Thank you. We just have a few more questions for you. So once we've extracted our DNA, what do you do with it after?
Depends on if you want to look at like a specific genes, we could also take those DNA and search for a specific gene inside those strawberries. So it's very useful to detect like new maybe like a not new organism. You kind of want to sequence find out what's exactly inside this genome.
Yeah, we actually know surprisingly little about what's in our own DNA. There's a lot of mysterious stuff that makes up our DNA that we actually don't know what the function is, for example. So there's scientists who try and figure out what the function of specific DNA is, and that's kind of what Ho-Yin is talking about as well, is trying to figure out what makes up that DNA and what it does.
Sounds like a lot of unknowns and a lot of exciting research to be done. And our last question for you today was coming from an attendee. If we do a gene test as a kid, then as an adult, will they be different?
That's a very interesting question.
Well,
I thought so too.
There will be a small difference because over time your cells does not replicate your DNA perfectly. It's not 100%. There might be some errors, and that's actually how cancer. One of the mechanisms of how cancer can arise, because sometimes replication, some mistake, you lose some information, then your cells become activated and just keep proliferating. Yeah.
Yeah, and it also depends on what kind of gene, because like you mentioned, like setting off like a gene test kit, it depends on what kind of gene as well you're looking at. So some of them, they might not really change as you age, and some of them, they're like Ho-Yin said, they're affected like by age. So the more times they replicate, the more likely over time there might be some sort of mutation that occurs, so a mistake inside your DNA that changes a whole lot of things, so like how cancer develops.
A large portion of our DNA is contained no information really.
Yeah.
It's some say it might be ancient viruses that are integrated into our DNA. So that that'll be another mechanism actually. Is some virus, they can potentially integrate into your DNA, and that will change your DNA. And that's also another mechanism of how some cancer can arise because of a virus.
Yeah.
I think cervical HPV. Yeah, I think that's yes. So yeah, cervical cancer.
Very interesting, and lots of exciting things to look into. Well, please, again, everyone, just thank you guys again for such a wonderful presentation, and that was a great demonstration. I can't wait to try it at home. Thank you so much.
Thank you.
Thank you.
Bye-bye, everyone.
Okay, and we have one more presentation before we take our second break. We will now have the Canadian Blood Services join us with their activity, The Power of Blood. As a reminder, once again, if you have any questions for our speakers, please post them in the Zoom chat and we will answer them if there is time. Canadian Blood Services, please take it away.
Thank you so much for having me. Can you hear me okay?
Yes.
Awesome. Sorry, I don't use Zoom often. So I'm just going to share my screen here. So I am very excited to be here. Thank you so much for having me. I am going to apologize in advance. I have contracted a cold for the first time in 2 years. So if my voice gets a little raspy, my apologies. But I do want to start off with a little bit of a land acknowledgement. So I am located in Toronto. Probably an introduction to. My name is Rachel. I am the Community Development Manager for Canadian Blood Services here in Toronto. And I would like to acknowledge that I am on the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. I'd also like to acknowledge that Toronto is now home to many diverse First Nation, Inuit, and Métis peoples. So what I'm going to be talking about today is I'm going to be going through a little bit, just a quick overview of Canadian Blood Services, and then we're going to get into blood, what actually makes up your blood types, and kind of like percentages and actually donation eligibility for different blood types. And then if anybody's interested, I'm just going to give a brief overview of how the donation process goes, and then we're going to play a fun Kahoot at the end, and the top 2 winners are actually going to be receiving gift cards from Canadian Blood Services. So stick around for that and hopefully pay attention because some of the questions are in the presentation. So just a quick overview of Canadian Blood Services. We were founded in 1998 based off of the recommendations from the Crever Report following the tainted blood tragedy. We're dedicated to improving patient outcomes through the manufacturing and delivery of safe, relevant, quality products and services to Canadians. Volunteers, partnered organizations, community groups, generous donors, and employees make our work possible. We're the connection between the sincere generosity of donors and the heartfelt appreciation of recipients. And we provide various products to Canadians, such as donated plasma that touches the lives of families of thousands of patients who require life-saving therapies and treatments made from plasma-derived protein products. Stem cells, specifically blood stem cells, which are immature cells that can develop into any cell present in the bloodstream. These are quite often used in blood cancer treatments. We also work with the organ and tissue donation and transplantation community to develop leading practices, professional education, public awareness, and data analysis and reporting. And then we also manage the blood supply for all of the provinces and territories except for Quebec. Quebec does have their own entity called Héma-Québec, but we do work very closely with them. So now let's talk a little bit about blood and what actually makes up your blood. So you can kind of think of your blood as a fruit smoothie with 4 basic ingredients blended together, and all of them are very important. So you have your red blood cells, your white blood cells, your platelets, and your plasma. Blood cells are produced in the marrow of your bones, especially in the vertebrae, the ribs, the hips, the skull, and the sternum. The unique cells called stem cells are the parents of all cells. So before your cells become blood cells, they start off as stem cells. But these essential blood cells fight infections, they carry oxygen, and they help to control bleeding. So we're going to start off with looking at plasma. Plasma is a critical part of the treatment for many serious health problems, and this is why we have a lot of blood drives asking people to actually come and donate plasma. And plasma is quite often the forgotten part of blood. The white blood cells, red blood cells, and platelets are important to bodily function, but plasma also plays a key role. Along with water, salt, and enzymes, plasma also contains important components. These include antibodies, clotting factors, and the proteins albumin and fibrinogen. When you donate blood, healthcare providers will separate these vital parts from your plasma, and then these parts can be concentrated into various products. The products are then used as treatments and can help save the lives of people suffering from burns, shock, trauma, and then any medical emergencies. The proteins and antibodies in plasma are also used in therapies for rare chronic conditions. These include autoimmune disorders and hemophilia, and people with these conditions can live long, productive lives because of these treatments. So some of the health organizations actually call plasma the gift of life for all that it can do. Plasma makes up the liquid portion of the blood. It's about 90% water, but it makes up more than half of the total blood volume. So it's about 55% of your blood volume is plasma. The other 10%, so the part of the plasma that isn't water, is the protein molecules, including the enzymes, clotting agents, immune system components, and other bodily essentials, such as vitamins and hormones. After we collect your plasma from your body, we can actually store it for up to 1 year before it's used. Plasma is very important. Next, we have your platelets in your blood. So platelets are the smallest of the blood cells. They are the sticky cells that clump together to form clots to control bleeding by sticking to the lining of your blood vessels. When in their non-active form, they are literally shaped like plates, which is where you get the name platelets from. A blood vessel will send out a signal when it becomes damaged, and when the platelet receives that signal, they'll respond by traveling to the area and then transforming into their active form to make contact with the broken blood vessel to help create that clotting. To make contact, the platelets will grow long tentacles that resemble a spider or an octopus to be able to stick onto the blood vessel, which is pretty cool. Once we collect the platelet from your body, it can only survive for about 5 days outside of the body. So that's why we need blood donors in all the time, donating both platelets, plasma, whole blood. That way we can keep replenishing our stores of these blood products and we don't run out. In your circulatory system, platelets only stay in it for about 10 days and then they're removed by the spleen. But of course, your body's creating new platelets all the time. On average, you need about 4 to 8 people donating regular whole blood. So this is just a regular donation to receive the amount of platelets that one patient would need. That also equals out to 1 apheresis donation. So we do have a separate donation process if somebody is interested in donating platelets and plasma. These are the same processes where we'll actually take your blood, we will put it through our apheresis machine. So you'll sit there for about 45 minutes with a needle in your arm. I actually just did this on Thursday and it went very well. We'll take the whole blood out and then we'll put it into our centrifuge and kind of separate out the platelets or the plasma, whatever we're looking for to receive. And then we'll put your whole blood back into you. So we're only taking that one component from your blood that's needed the most for that donation. So it's a pretty cool process if you ever get to see it. Then we have the white blood cells in your blood, and the white cells are the body's primary defense mechanism against infection. They can move out of the bloodstream and reach many tissues being invaded by microbes and foreign bodies. So these ones help to fight off some illnesses. And then finally, we have our red blood cells. So our red blood cells are responsible for transporting oxygen from your lungs to your body's tissues. Your tissues will produce energy with the oxygen and then release a waste identified as carbon dioxide. Your red blood cells will take the carbon dioxide molecules to your lung so that you can exhale them. The red blood cells actually make up about 40% of your blood, and they contain a molecule called hemoglobin, which carries the oxygen and makes the blood red. Your red blood will live for about 120 days in your blood system. and they'll be removed from the spleen. But of course, you're creating new red blood cells all the time. After your donation, your red blood cells outside of your body will only survive for about 42 days, but usually they'll be used by patients before that. The red blood cells are most needed for patients with significant blood loss through trauma, surgery, or anemia. So now we're going to look at blood types. So everybody has a type. You belong to one of the 4 blood groups, which are O, A, B, and AB. We do also have an additional Rh factor on blood that determines whether your type is positive or negative. So if you have this rhesus factor on your blood, it means your blood type is positive. So if you have it, you're type A, you're A positive. If you don't have it and you're type A, you'd be A negative. So that just factor determines you're positive or negative. Knowing your blood type is super important because it determines who you can donate blood to, but also who you can receive blood from. So if you take a look at this chart over here on the left, and hopefully you guys can see the laser pointer that I have going, you can take a look at who can receive blood types and who can donate blood. So if you take a look at AB positive up here at the top, it can receive blood from everybody. So AB positive blood is a great blood type to have. Because it's positive, it can receive blood from everybody. Where you notice AB negative can only receive blood from the negative blood types. That's because when this Rh factor is introduced to negative blood, it could have a negative reaction. So I am A negative. If I was to receive A positive blood, I wouldn't have a very good reaction to the blood and it wouldn't really be helping me out. But A negative blood can donate to A positive blood. So having this non-Rh factor blood donated doesn't make a big difference to the positive blood type. So if you take a look here again, AB positive can receive blood from everybody. AB negative can only receive blood from the negative blood types. And the AB can receive blood from everybody because O can give to everybody. O is just the absence of a blood type, so they can really give to everybody. And then the Bs and the As are the actual blood types. So AB means you have both blood types. You can give to, you can receive from everybody. And then you can look, we have the A blood. So of course they can't receive from B blood because they don't have that B factor, but they can receive from the O's and then the A's. And then if you take a look down at the bottom, we have our O's. So O's can only receive from O's. They cannot receive from anybody else, but they can give to everybody else. So O positive can only receive from O positive and O negative can only receive from O negative. And when we look at this chart over here on the right, the percentage of blood types in Canada, you can see that O negative, it can only receive blood from itself, but it can give blood to everybody else. So it's used in a lot of trauma situations. Since it can only receive blood from itself, and it's only 7% of the Canadian population, we are in desperate need of having O negative blood all the time to make sure that when people do come in with O negative, so let's say somebody with leukemia who needs up to 8 donors per week needs O negative blood because they are O negative, we have to make sure that we have that on deck for them and aren't just using it constantly. People also do tend to have better reactions when they're given their own blood type for their therapy. So it's always good to have all of the blood types on hand for that. And if anybody's ever curious about what your percentage of your blood type is, you can take a look over here at the side. So our most common blood type is O positive, which is really good because as we know, O positive can give to all of the positive blood types. So it's great to have that abundance of O positive blood. It's also used in trauma situations for positive blood types, so it's always needed as well. And then we're followed by A positive at 36% of the population. Then we have B positive at 7.6%, O negative at 7%, A negative at 6%. And then we go over here to the more rare ones that we can find. So we have AB positive at 2.5%, but that's okay because remember, AB positive can receive blood from everyone. And then AB negative, our most rare blood type, 0.5% of the Canadian population. But again, that's okay because it can receive blood from all the positive blood types. But of course, it is still desperately needed for people with those blood types undergoing regular treatments. And then we have our B negative at only 1.4% of the population, and it can only receive blood from O negative and B negative. So we want to make sure that we have lots of stores of all of these blood types to treat Canadian patients. So now I'm going to talk just quickly about our rare blood program. So Canadian Blood Services does have a rare blood program. So, which means, of course, that some people's blood is rarer than others. It's not just about being type A, B, O, or AB. On the surface of our red blood cells are molecules called antigens, and there are about 360 known antigens, and some combinations of antigens are far less common than others. So whenever a blood transfusion is required, of course, time is of the essence. But if somebody in need has a rare blood type, finding a matching donor can be really hard. So through our rare blood program, we make sure that life-saving rare blood is available to all patients whenever and wherever it's needed. You are considered to have rare blood if only one person in 500 has the same combination of antigens as you do. And if only 1 in 1,000 people has your same combination of blood, it's considered extremely rare. If you're a regular blood donor, we may have already determined if your blood is rare or not. We often test donated blood when we identify a patient with long-term illness who has an ongoing need for a specific rare blood type, or if there's an overall shortage of a certain blood type in Canada. So we don't do the rare blood testing for everybody's blood, but when those situations pop up, we will be testing certain blood types to make sure that we have the rare blood on hand. Because antigens are inherited, kind of like your eye color or your hair color, we also follow up with family members of known rare blood donors or blood patients with rare blood types. That way we can target our specialized testing to those who are most likely to have rare blood. So that is our rare blood program. It's a really cool program that we run here. I've actually run into a few donors that have ended up having rare blood. So it's very neat to see. And we do keep the rare blood kind of stocked in freezers just in case something comes up. So I talked about blood and blood donations I talked about blood and blood types. Now I'm just going to quickly talk about the need for blood. And feel free to put your answer to what you think it is in the chat. I'm just going to ask, how often does somebody in Canada need blood? Do you think it's every 30 seconds, every 60 seconds, or every 90 seconds?
Rachel, the answers will be in the Q&A section. Are you able to see that?
Oh, perfect. Yes. Amazing. Thank you. I see 2 30s. It's actually every 60 seconds. So every minute of every day, somebody needs blood. Last question. What percentage of eligible Canadians donate blood? So out of everybody in Canada that is eligible to donate blood, so it meets the eligibility screening requirements, how many actually do donate blood? Is it 4%, 14%, or 24%? I see somebody already got it. It is 4%. So less than 4% of eligible Canadians are keeping Canada's lifeline going. That's a very small number, keeping Canada's blood supply intact. So since we talked about the blood types and everything, let's just talk like how can our blood actually be used to save lives? So we do need over 112,000 new donors every year to meet the needs of Canadian patients. And how this blood is used, so under cancer treatment, somebody can use up to 5 blood donors during their cancer treatment. Someone with leukemia can use up to 8 blood donors per week. Someone undergoing brain surgery can use up to 2 donors. Somebody with a blood disorder can use up to 4 blood donors per month alone. A car crash victim can use up to 50 blood donors. That's 50 people that need to be donating blood regularly to treat one person. Somebody undergoing heart surgery can use up to 5 donors. And somebody with internal bleeding can use 2 to 8 blood donors per week. So this is a lot of blood that we need constantly to help save lives every single day. So I am just going to quickly walk through the blood donation process. I won't spend a lot of time on this, just for anybody that's curious about donating and how they can help. So as you come in to donate, of course, you need to book an appointment ahead of time, and you can do that through various ways, which I'll talk about in a moment. But you book your appointment, you bring a piece of government issued ID, so driver's license, health card, passport, any of those work. You want to make sure that you eat lots of food beforehand and especially have a nice salty snack and drink lots of water before your donation. And then once you get to our donor center, we're going to take you through a wellness check where we're going to check you, just ask the basic COVID-19 questions that you kind of go through everywhere you go. We are going to get you to put on one of our Canadian Blood Services medical masks that you can just wear throughout the process, just because at some instances, physical distancing isn't possible. Of course, when the needle is going into your arm, not possible. And then you're going to check in with one of our donor services representatives. And if you haven't donated blood before, of course, we'll make you a donor profile at that time. If you have donated blood before, we just kind of check in to make sure that our staff knows that you're actually there. And then you're going to read a pamphlet, and that's just everything that you need to know to donate blood. And then you're going to complete a donor questionnaire. This is about 60 questions on travel, lifestyle, medications, everything like that, just to make sure that you're okay to donate. And then you're going to undergo an interview. I apologize, I just need to call. You're going to undergo an interview where we're just going to go over this questionnaire with you just to make sure that everything was answered correctly. And then we're going to test your hemoglobin levels. So as you remember, your hemoglobin is located in your red blood cells. Just to make sure those levels are okay for you to donate, we're going to take your blood pressure and your body temperature as well, just to make sure that everything is safe, you're nice and healthy and okay to donate. And then you are going to sit back, relax, and donate. The time with the needle spent in your arm is only about 10 minutes. That's usually the maximum time. So you're usually there for about 5 to 10 minutes. It's a very easy process. And then after you donate, we're going to apply a pressure bandage just to make sure the bleeding is stopped there and it's nice bright color blue or red. And then you're going to hang out for about 5 minutes in a nice physically distanced area just to make sure that you're feeling okay before you head out. And then we're going to provide you with a drink and a nice snack to help you rehydrate after you've left the building. So that is the blood donation process. And if anybody is interested in booking an appointment, we do have an immediate need for blood right now. Please, if you can, book an appointment to donate. And you can do that through blood.ca, our Give Blood app, or you can give us a call at 1-888-2-DONATE. And then just some common questions that we come across for donation. So how long does the blood donation take? The whole process takes about an hour start to finish, and that's from checking at the wellness station all the way to picking up your snack at the end. And again, as the time with the needle in your arm is about 5 to 10 minutes. How much is it taken during each donation? So approximately 450 milliliters or 1 pint. You do have about 10 pints of blood in your body, so losing that 1 pint will not make a difference. If you're interested in ever booking a group, coming together as friends, you can contact me. And then how will you feel after donating? Most people feel really great, but there are some things that you can do to help. So making sure that you eat lots of food beforehand, drink lots of water, you get a nice good night's sleep beforehand. All of those will really help your donation. And then this is a question that we run into quite often. Can you donate if you consume cannabis or alcohol? Yes, but you will not be able to donate if there's evidence of being intoxicated while you're at your donation, because you need to be able to give informed consent. And of course, you are not informed if you're intoxicated. So you can drink and consume cannabis before your donation, but you just can't be intoxicated while you're actually at your donation appointment. It doesn't affect your blood at all. It will make you feel dehydrated if you are drinking beforehand, though. And now we are going to play a quick Kahoot, and then if there's questions, we can get to those. So I'm just going to stop sharing and share that screen there. Let me know if you can see that.
Looks good.
Perfect. So anybody that wants to join, the code is at the top, and there's also a QR code. Make it a little bit easier to enter. And the top 2 people are going to win a prize. So I enjoy the platelet name. About 5 more seconds and then we'll get started. All right, we will start. So first question. How many new blood donors are needed every year to meet hospital demand? Amazing. Great job, guys. You paid attention. Love it. Awesome. All right. Someone with O positive blood can donate to perfect. All positive blood types. Great job. We still have 1 liter, Cabby Car. Great job. How many eligible Canadians donate blood? So this one is my fault, guys. I know I gave you the 4% number, but this is for plasma, platelets, and whole blood. 1 in 81, perfect. You guys must have seen our ads. Great. What is the most common blood type in Canada? Great. All right, and how many blood donors are used to help treat somebody with leukemia? Perfect. And last question, how often does somebody in Canada need blood? Amazing. Good job to Cabby Car for keeping up that #1 spot the entire time. Okay, so I'm gonna, goodness. Not sure if I'm still sharing my screen or not.
Yes, we can still see it.
Okay, perfect. I'm gonna re-put up my email for the 3 top winners there. So you can, if you could just send me an email and I can collect your address from you to send you out these gift cards.
Thank you, Rachel. Do you mind if I ask you a few questions we have from the attendees?
Absolutely, please.
Okay, so we had a few questions about if anyone could donate and who would be eligible to donate.
Perfect. Yeah, so we do have various eligibility, and all of our eligibility can be found on blood.ca under ABCs of eligibility. But just the basic eligibility is you need to be at least 17 years old. You need to weigh at least 110 pounds to be able to donate, just because if you weigh under that, you don't yet have enough blood in your body to be able to safely donate. You have it in sorry, you have to make sure that you haven't traveled outside of the country in the past 3 months. Of course, there are a lot of limitations to that. So if you've gone to the United States, there's no malaria risk in the United States. That's totally okay. So you just have to check that out on blood.ca. You can't be pregnant or had a baby in the past 6 months. And then there's just various other eligibility requirements, such as if you're taking any medications. There's lots that you can still donate on. So don't be kind of like put off like, oh, I'm taking a medication, I can't donate. That's not true. There's lots of still like options for you to be able to donate as well. So you just kind of have to check out our website to see your eligibility.
Fantastic, thank you. And we have another question here. Does blood expire?
It does. So after 42 days, your blood will expire. Typically it is used up before then though.
Very cool. We have a question here. How often can one donate blood, and particularly if you are a woman?
Perfect. So women can donate every 84 days. Males can donate every 56 days. That's just for whole blood, but for plasma donations, women can donate every 2 weeks and men can donate every week.
Very cool. And I have one final question for you. How close are we to having lab-grown blood?
That is a fantastic question. I was actually looking into that last week. So I know we were doing some research studies out in Vancouver, but I'm not sure where the state is at for that. So I apologize, I don't have the full answer for you, but if you wanted to send me an email at the email that's on the screen, I can look into it some more and get back to you on that.
Perfect. Well, Rachel, thank you so much. That was very interesting. I really enjoyed your presentation, and congratulations to our Kahoot winners.
Amazing. Thank you. Yes, if the winners could just email me at the email on the screen and I can collect your information, that would be wonderful. And thank you so much for having me. I really appreciate it.
Fantastic. All right, before you go, is it the top 2 or top 3 winners?
We'll do the top 3.
Thank you.
Of course.
Okay, great. And I'll just give us a minute here. We will be going on our last intermission break, returning at 2:10, but just a quick reminder that over the break, you can leave your Zoom webinar on and you do not have to exit the webinar itself. So once again, we'll be taking a break now, and please return at 2:10. Welcome back, everyone. We now have our final two presentations for this webinar, starting with the University of Toronto Department of Physics joining us with their activity, the U of T Physics Virtual Tour of Snow Lab. As a reminder, if you have any questions for our speakers, please post in the Zoom chat and we will answer them if there is time. Physics, please take it away.
Hi, everyone. My name is Dr. Miriam Diamond, and these are my little research assistants. This fellow is named Quark. He's named after a subatomic particle. And this little fellow is named Qubit, short for quantum bit. And we will be hearing a little more about their namesakes in just a few minutes. And as you can hear, they say hello and thank you very much for coming. So I'm going to start with a very brief introduction to what is particle physics. Well, particle physics is essentially the study of the most fundamental building blocks of the universe and how they interact with each other. I'm going to share my screen with you now to show you the standard model of particle physics. So this is our current theory of essentially all the different types of fundamental building blocks. You can think of them as like different Lego pieces. We have one category of Lego pieces called quarks. They come in 6 different types or flavors, which we rather whimsically named up, down, charm, strange, top, and bottom. My little quark here, of course, likes to think he's a charm quark. And then we have what are known as leptons, of which there are also a few different types. We have electrons, muons, and taus. And then there are rather mysterious and elusive little partners to each of them called neutrinos. There's an electron neutrino, a muon neutrino, and a tau neutrino. And as far as we have been able to observe in the laboratory so far, this is what matter is made out of. Then there are also force carrier particles. So there's the electromagnetic force, which is carried by the photon. There's the strong force, which is carried by the gluon. There's the weak force, which is carried by W and Z bosons. And the most recent piece of the standard model to be experimentally discovered is called the Higgs boson, and it was found about a decade ago using a super collider called the Large Hadron Collider at CERN. So this model has been very successful, but we know that it is still incomplete. Why is it incomplete? Well, there's something else out there that we don't quite know what it is called dark matter. And there's something else yet called dark energy. And I have devoted most of my career to dark matter research, or as I call it, join the dark side beyond the standard model. Now, I know that it's a few days past Star Wars Day. It's not quite May the 4th be with you. It's a few days late for that, but it is not too late to join the dark side research. What exactly do I mean by the search for dark matter? Well, I mean that most physicists have now come to the consensus that there is some sort of other subatomic particle out there, or maybe several other subatomic particles that are not yet included in the standard model that make up stuff that we can actually find evidence for its existence from astrophysics observations. So when we look at, for example, galaxies and clusters of galaxies and how they move, it seems that in order to move that way, there must be much more matter in them than what we can see. And so we surmise from this, there are extra particles out there floating around that do not interact with photons. In other words, do not interact with light. We cannot see them with our eyes, hence dark matter. So if we cannot see them directly, how do we try to search for them in the lab? That is where my research comes in at a place called SNOLab. And we are very, very lucky here in Canada to play host to one of the world's premier astroparticle physics facilities. As you can see from the slogan here, we explore new frontiers in deep underground science, including astroparticle physics. So you might be wondering, wait a minute, we were talking about outer space and subatomic particles and stuff. What does this have to do with deep underground, and what's this SNOLab thing? Well, essentially, SNOLab is a scientific laboratory buried 2 kilometers underground. And the reason that we built a lab that far underground in what's actually an active nickel mine is that we need very, very sensitive particle detectors in order to try and find these dark matter particles. If they do in fact exist, they would go right through normal matter almost all of the time without even leaving a trace of its existence. The hope is that every once in a while, when a dark matter particle wanders through our detector, it has a very, very feeble interaction with the ordinary matter in the detector, and that's what we would pick up. But if we put these particle detectors pretty much anywhere on the surface of the Earth, the tiny, tiny signal from the dark matter interactions will get completely swamped by all sorts of other things that are going on, such as cosmic rays that are constantly coming down from space, radio waves from things like radio stations and telecommunications. So in order to shield ourselves from all that, we put our apparatus as deep underground as possible, where the rock provides us with natural shielding. So not only do I encourage people to join the dark side, I encourage them to join our secret lair deep underground at the bottom of a mine shaft to essentially take over the dark sector. All right, so a little bit more about the history of this SNOLab place. It originally started a few decades ago as one experiment known as the Sudbury Neutrino Observatory, looking to find out more about these rather mischievous little standard model particles called neutrinos. So neutrinos, even though they're now part of the standard model, took us several decades to actually find because they also interact very, very feebly with what most of normal matter is made out of, which is electrons and up and down quarks that make up the protons and the neutrons in atoms. And so this was one of the first deep underground experiments to search for elusive subatomic particles. I have my little neutrino subatomic particle plushie here, and it is wearing a little burglar mask. Why is it wearing a burglar mask? Well, because it's so sneaky. It can sneak right into your detector and sneak right out again without you even noticing that it was there. Our attempts to catch the burglar at Sudbury Neutrino Observatory were wildly successful, and in fact, it led to the then director of the observatory, Dr. Art McDonald, winning the Nobel Prize for Physics a few years ago. And so then following up on the success of SNO, we built a whole additional experimental space around it with room for more astroparticle physics experiments to let us learn more about neutrinos and also search for these dark matter particles. And for the dark matter searches, we can use a lot of what we learned from the neutrino searches and essentially take them to the next level. So I'm now going to show you a couple of videos about SNO Lab, and then I will take you on a virtual tour of the SNO Lab facility. So I'm just going to stop my screen share and restart it here so that I can share the sound and optimize for video. Here we go. All right, so welcome to the deep underground layer of SNO Lab.
Breaking news. Sources tell us about strange happenings deep underground near Sudbury, Ontario. Could it be a secret underground government facility?
No secrets, just science. Welcome to the Sudbury Neutrino Observatory, SNO Lab for short. It's here where groundbreaking astroparticle physics research is happening, right under our nose and feet. Most of the experiments here at SNO Lab are located deep in the Earth's crust, over 2 kilometers down. Away from cosmic radiation, the very sensitive experiments are looking to understand more about our sun and the universe. Following the success of SNO, the experiment that helped prove neutrinos have mass, solving the solar neutrino problem, SNO Lab was formed. The available space for experiments has increased dramatically, allowing many more projects to take advantage of the unique location. With the expansion, SNO Lab will reach 5,000 square meters of clean lab space for experiments and supporting infrastructure. Many of these experiments are trying to learn more about the tiny particles that we can't see or feel. They're called WIMPs, weakly interacting massive particles. Scientists think they may be the best candidate for dark matter, the mysterious stuff that makes up a large portion of the mass in our universe. Picasso is one of these experiments, and it's looking for one type of WIMP called neutralinos, a particle that scientists predict might exist. Inside the water shield, Picasso's detectors contain tiny droplets of superheated liquid suspended in a gel-like material. If a WIMP interacts with molecules in the unstable liquid, the droplet explodes into a larger gas bubble, creating a small vibration that is then analyzed to learn more about the WIMP. Also on the search for WIMPs are the deep and clean experiments. These are located in one of the newest areas of the lab. Deep and mini-clean will use liquid noble gases to search for WIMPs. A WIMP will occasionally interact with the molecules in the noble gas and create a small flash of light that is collected by super-sensitive light detectors. With a similar design, the original SNO experiment used a heavy water detector to solve a long-standing mystery in the physics world. The sun didn't seem to be creating as many neutrinos as predicted. SNO detected the missing neutrinos and solved the solar neutrino problem. SNO Plus, an experiment using the SNO detector, will be able to detect even lower energy neutrinos. It will use a special liquid scintillator instead of the heavy water. This change will make it more sensitive and could determine the mass of the neutrino. The Helium and Lead Observatory, called HALO, is used to detect the large amount of neutrinos given off by a supernova. The neutrinos from supernovae reach Earth hours and sometimes days before the light does, giving astronomers a heads up that a supernova may soon be visible. HALO is one part of the Supernova Early Warning System, which links neutrino detectors around the world to astronomers. These experiments, among others, now reside in the newly expanded SNO Lab. The research done here may well revolutionize our current understanding of physics and the fundamental way our universe works.
as we learn more about the neutrino.
The Earth is constantly being bombarded with all sorts of junk coming in from space. We come underground because we have 2 kilometers of solid rock over our head. So that filters out all of that stuff that we don't want and leaves us only the stuff that we actually want to see.
So today we're in this little town in northern Ontario, and it's very early, it's still dark, and it's snowing. It's not even 6 a.m. We're about to get in the car, and we're gonna go to this mine where we're gonna actually travel deep underground and visit this lab that's one of the deepest labs in the world. And down there, they're looking for these little particles, these tiny bits of matter that make up the entire universe.
Scientists at SNOLAB are probing the sun and distant stars for clues about how it all came to be, and our cameras were given a rare chance to check it out. But getting there takes a while. First, we dress like miners.
Is that Instagrams?
My upright vibrates every time I slouch, which
Oops, my apologies. It seems to have decided to play some ads in the middle. Just a moment.
That's okay. It happens to us all.
Yeah.
Ads just love to pop up.
Okay, there we go. Got rid of that again. I thought I had the ad blocker all working, and I guess not so. Okay.
To almost 7,000 feet.
So right now we're 2 kilometers underground in an active copper and nickel mine. We're hiking another 1 or 2 kilometers through the mine to get to SNOLAB, which is actually one of the cleanest lab spaces in the world.
We can't track in any dirt, so while our gear gets wiped down, we're sent to take a shower and change our clothes. Now for the science. These scientists are being lifted out of a massive cavern filled with ultra-pure water. It's shielding a detector looking for neutrinos, also known as the ghost particle.
Okay, so we're here at the Snow Plus experiment. This is what's down that hole. Like, what are these photos? This is beautiful.
So these are photos of the detector of our acrylic vessel, which is the center of the detector.
Why should we be looking for neutrinos? Why do they matter?
They're a very good messenger of the reactions that create them. We've been studying them for decades and still have more questions about them.
Discoveries made here won the Nobel Prize in Physics in 2015 by revealing that neutrinos from the sun had mass. Now, Erica and her team are expanding their search.
What are you guys looking for?
We'll be looking at neutrinos from the Earth around us, geoneutrinos, neutrinos from reactors in Canada, so that can tell us more about what's going on in the sun than the light, which takes millions of years to get out.
Wow, so we can actually study the sun from deep inside a mine.
From 2 kilometers underground.
That's so cool.
Then there's dark matter. No one has ever found it, but it's the glue holding galaxies together, and this device could detect it.
This is PICO. This is what we're using. It's the same that's actually inside there.
What is dark matter?
Right. So dark matter is, well, basically something that we don't know what it is. We don't understand about a quarter of the universe, so about 27% of the matter that's out there, we have no idea what it is.
But it's down here in this mine?
It's down here in this mine. It's all the time. It's going through us all the time. It's going through the Earth. And it'll interact only really rarely, which is, of course, it's a great thing in that, you know, it makes it down here. We can filter out everything else.
So do you think that someone, maybe hopefully you guys, will find dark matter soon?
I'm really hoping so, yeah. We're getting to the point now where the limits are being driven down so far that if we don't find it soon, we're not going to find it for a while. We're going to have to think of a new way to detect it.
That's a lot of pressure, and with so much at stake, there are plenty of rules at SNO Lab.
So about 50 people work down here every day, and there's no cell phones allowed, there's no Wi-Fi. Could actually set off detonations far off in the mine, so you have to be really careful.
Even opening the wrong door could compromise an experiment. And not everyone down here is a scientist.
I've heard, that your job is as important as the scientists inside.
It's more important almost, because if it's not clean when it goes in, their experiment will not work. It will fail.
Wow.
Because dirt is the enemy.
Everything that we see in SNO Lab today has been down that cage and through this car wash before getting into that lab.
That's right.
Every single pipe that we see here.
Every single pipe has been, beams of steel, roll of toilet paper, it doesn't matter.
Blue sticky mats prevent shoes from spreading contamination. The walls.
All right, so that was a brief video intro to SNO Lab. What I'm going to do next is take you on a virtual tour that we also constructed for VR virtual goggles. So if you go to the SNO Lab website, and if you have something like Oculus Rift, you can do the same thing that I am about to do here, but in 3D. So here is what you see when you first come down into SNO Lab. I will bring up the overall map here that shows you the layout of the facility. When you come down the cage, in other words, the elevator that goes all the way down the mine shaft, you find yourself at point 1 here, which is what we call the drift. Why is it called the drift? Well, not because things are drifting around. In fact, quite the opposite. Everything here has to be well organized. You might not be able to tell from these images here that things are actually very carefully cataloged. We have to know exactly what is down here and exactly where it is. It's not just random piles of stuff. No, drift is the term that we use for a segment of tunnel underground. And from the drift, the first place you go is into the so-called car wash. It's not actually a car wash, that's just our nickname for it. But this is the place where, as you saw in the video, everything has to be very carefully cleaned when it's first brought underground. So every single little piece of equipment, as well as every large piece of apparatus, has to go through here. And after the very careful cleaning process, you can then take it through the staging area and through the main hall. So I will show you on the map here where we are right now. We're now at point 10 here. And so you can go off in different directions now, depending on what experiment you are going to. One of the most fascinating and most spectacular places to see here is the SNO Plus experiment, which is being carried out using the infrastructure from the original SNO project. So if you go down a hallway here to what's labeled here as point 18, this is the control room for the SNO Plus project. So this is where someone like me sits behind a computer for something like 8 hours at a time, watching a real-time reconstruction come in from the particle detector that shows us exactly what's going on in it. Then through the control room is the deck, where we store pieces of hardware and electronics for data acquisition and maintenance and so on. And on the other side of the deck, this is the actual SNO vessel. This is a giant tank. Used to be filled with heavy water. We then emptied it of the heavy water and filled it with scintillator. While it was empty, we put some cameras down there and we put some people down there also to renovate it. So for scale, this is the size of a person. And this is the detector. Yeah, so the deck is so the deck that you previously saw was all the way up here. And then the vessel comes down from the deck and it's a long way down. And then underneath the vessel is a support structure. And what are all these things? These are called photomultiplier tubes, or PMTs. And these are what actually pick up tiny flashes of light that come from the detector when particles like neutrinos or dark matter wander into it and have a very feeble little interaction. And here's a view from the other side of what the outside of the detector looks like. And again, for scale, there's a little person standing down there. So SNO is actually the first major particle physics experiment that I ever worked on. And the ones that I'm working on now are actually the dark matter searches. So they are located in other hallways here. I will take you down to a couple of them. There's one that you saw in the video called PICO. And the actual apparatus that detects the particles is inside this shielded tank. And then what is all this stuff? Well, there's all sorts of purification and cryogenics and pressure vessel equipment that is required in order to keep the conditions inside this tank just right for the experiment to run. So then I will take you to another area here called the Cube Hall. This is when you sort of come down the hallway, approaching it. And then if you get to the railing and you look over the edge, ooh, don't look down, might make you dizzy. These are all sorts of other dark matter experiments, including DEEP and mini-clean. So this is a view of the deck from the DEEP side. The apparatus is all back here. And this is a giant tank of liquid argon. Yeah, we use liquid argon in the detector. And if it's used up, what happens? It's all gone. So this is a view of the upper deck. I can also take you down to the lower deck. So this is the bottom part of that tank that you saw earlier. So you can see just how large some of this apparatus is. Woo! And you get a good workout if you have to climb up and down these ladders all day. Then the experiment that I spend most of my research time on right now is called Super CDMS. CDMS is short for cryogenic dark matter search. At the time that we took the photos for making this virtual tour, we hadn't yet started to install most of the equipment. So right now, it just looks like a big empty space. What my team has been spending a lot of time on is actually installing the components down here. And we are looking for various different possible types of dark matter particles. So I have a little bag of dark matter candidates here, such as axions and dark photons and weakly interacting massive particles. And based on astrophysics observations, we think that the dark matter density should be such that if I have a box approximately this big, there should be one dark matter particle in it. So the question is, what type of particle exactly is it? And can we find it down here? So that is our mission in order to explore the dark side and take over the galaxy. All right, thank you, everyone.
Thank you so much. That was very interesting. And we love all your little plushies there. They're great. We have quite a few questions from the audience, if you don't mind.
Yeah, sure.
The first question is, how do you know those subatomic particles / quarks exist? What kinds of evidence validates their existence? Do each give a distinctive signal or something like that?
Okay. So for particles of matter, we have actually been working for hundreds and hundreds of years to figure out what the most fundamental constituents are. If you look back to the ancient Greeks, for example, they thought that matter was composed of atoms, where they called the atom indivisible. And then eventually we found that atoms were not, in fact, indivisible. There were these little negatively charged bits, which we now call electrons, in them, and a positively charged part, which we now call the nucleus. We then figured out that the nucleus was made up of protons and neutrons. And then we figured out that the protons and neutrons were made up of quarks. And so how did we keep going down to these smaller and smaller pieces? Well, essentially, we smashed stuff together as hard as we could and watched it splinter apart into its tiny components. And we've gotten better and better over the years at smashing stuff together at higher and higher energy. So that's what we do at super colliders, such as the Large Hadron Collider. And so the higher the energy with which we can smash things together, the more fundamental the parts that it splinters into. And so we can now actually create what we call a quark gluon plasma at a super collider. We think this is what existed like in the very, very early universe, in the very first fractions of a second right after the Big Bang, when the universe was sort of unimaginably hot and dense and a lot of energy packed into a tiny area. And so then quarks are no longer nicely grouped into objects like protons and neutrons. Instead, they sort of float around in this soup. And we actually don't know for sure yet that quarks are the most fundamental things. Maybe there's even a substructure to quarks. And if we were able to go up to, say, 1,000 times or 1,000,000 times or 1,000,000,000 times the amount of energy that we have in the Large Hadron Collider, maybe the quarks would splinter into smaller things. We don't know. So it's a very good question.
Thank you. And speaking of those quarks and leptons, I'm very interested how they named them all. Do you have any insight on that?
So actually, with quarks, it's very cute. One of the physicists who first proposed their existence was a little bit whimsical and liked poetry. And one of his favorite poems was kind of a nonsense poem, sort of like Dr. Seuss or Lewis Carroll, and had a line in it, 3 quarks for Muster Mark. And it turns out that quarks like to pair up in threes. They don't like to be found by themselves. So for example, a proton is 2 up quarks and a down quark. A neutron is 2 down quarks and an up quark. So he saw this line and he was like, hey, some weird little whimsical thing that comes in 3s, quarks, perfect.
That's too funny. I like it. Yeah. Another question from an attendee. If the rocks underground shield everything, does it also shield against what you are detecting?
So it does not shield against everything. It shields against stuff that's made out of normal matter, stuff that's made up of standard model particles. But neutrinos and also dark matter tend to go right through, quote, ordinary matter. A neutrino can go through a light year of pure lead with a 50% chance of leaving no trace that it was ever there.
Wow.
Yeah.
And speaking of that, could you just reiterate why it's so important that everything is so clean in the SNO lab?
Okay, because otherwise you get essentially fake signals in the detector. So if you have some dirt, for example, it turns out that there's a very, very, very tiny proportion of the particles in dirt that are radioactive. We don't notice this on an everyday basis. You don't have to worry about it. But for example, if you eat a banana, bananas have potassium in it, and there's one naturally occurring isotope of potassium that's radioactive. Similarly, you might have heard of radon in people's basements. So there's all this naturally occurring radioactivity in pretty much everything around us, including rocks in the earth, which is where most dirt comes from. And so if you track dirt down into SNO lab, you're taking a few radioactive particles in there. And so the radioactive particles, when they then randomly decay, give off a tiny little signal that normally we wouldn't notice, but our particle detectors do notice. And this signal could be confused for a neutrino or dark matter signal.
Thank you. And have you ever been to SNO lab personally? If so, would you mind telling us about that experience?
Oh yeah, oh yeah. So actually, the very first time that I went down there, I was an undergraduate on a summer research internship project, and I have to say that going down the mine elevator for the first time took a little bit of courage on my part. It's a little bit dark and kind of claustrophobic. People are kind of crowded together, and it's a very strange sense when you sort of see and hear this rock whizzing past you as you're, going down into the depths of the earth. But I did feel safe because I was wearing full mining gear, including a hard hat, and I had a little harness on my back so that if somebody had to basically, attach a harness to my back and get me out somewhere, it was fine. We've never had an accident that has caused any serious injury or death down there. Canadian mining regulations are very strict. So once I kind of got over my fear and got down there, then I would say my least favorite part was having to actually walk through about 1 kilometer's worth of mine tunnel to get from where the elevator came to where the SNO experiment was. The reason that's not fun is you have to do that walk in your steel-toed boots. For women who have ever worn high heels, steel-toed boots are about as much fun, just the weight on the opposite end of your foot. Then once I got down there, I had to do this whole clean room thing where we change out of not only our mine gear, but our regular clothing that's underneath. Also, you have to take a shower, and then you have to change into all of the special clean room stuff that seems like a hazmat suit. So that's also not quite so much fun. But then once you emerge on the other side of the shower, you are in this totally clean environment. You would have no idea that you're actually like underground in a mine. And it's just, it's one of the coolest science labs you could ever possibly be in. I got to then go into sort of the little control room area, and yeah, it was a really fabulous experience. Hopefully post-COVID, we will get back to being able to do some public tours. So if you are ever in Sudbury, hopefully you can stop by SNOLAB or to a place called Science North, which is sort of a science museum, where they actually have sort of a replica model of a mine shaft, but not nearly as deep. So you just go, you know, a few tens of meters underground, but they have like a whole little mock setup there of a mine tunnel, and they have a lot of exhibits about SNOLAB. So even if you don't get to see the real thing, I would highly encourage you to go get at least part of the experience for yourself.
That's very exciting. And I think in the video it mentioned that there was an active mine there. Does that impact your studies at all?
So sometimes it does. We have, for example, seismic systems. So we put some of our devices on seismic platforms that essentially compensate for any little vibrations that might happen in the rock due to the mining activities that are happening nearby. And then we also have sensors that tell us, oh, there was a seismic tremor right now, so let's not count any data that comes in right now. We also have to cooperate with the mining company, which is called Valet, to make sure that, for example, when we're trying to bring some equipment underground, it's not the same time as they're trying to bring some mine equipment underground, and you know, we're both trying to use the same cage and everything. So it can be a little bit challenging from a logistics point of view, but Valet has been really fabulous in hosting us. And it's actually quite fun to sort of chat with some of the miners about what's going on down there. It is mostly a nickel mine, and there's actually some very interesting engineering challenges, things like geo-engineering and structural engineering issues that are associated with the mining side of it.
Very cool. We have a few more questions from our attendees. Someone asked, why is water used in the detector?
So as I said about neutrinos, they interact very, very feebly and hardly ever with normal matter. That being said, there's certain atoms which they are more likely to interact with than others. And it turns out that they like hydrogen. And so water is, of course, H2O. Also, it is cheap and it's abundant. So if you want to make a really, really, really large tank of some detector material, water is a good thing to use, but there is a catch. We weren't using normal water, we were using heavy water. And so heavy water has an isotope of hydrogen that the neutrinos like even more than regular hydrogen. It has an extra neutron in it. So this is called deuterium. Deuterium is not so abundant, not so cheap, but we were lucky because we got some on loan from Atomic Energy Canada. They actually used to use it in nuclear reactors. So we essentially got it for free.
It's always nice when that happens.
Yeah.
And so we had another question here, and they're just asking if all of these molecules go through, how do we measure things like neutrinos?
If which molecules go through where? So the goal is to have no signals in the detector, so nothing coming in and out of it except for the neutrinos and the dark matter. So we want to have nothing radioactive. We don't have light from the outside getting through that shielding and so forth. So basically the idea is that inside the detector, everything should be totally dark and quiet.
Awesome. And then we have two questions here. Are the clean clothes radioactively shielded? And do you need to be on a potassium-free diet before visiting?
No, you do not need to be on a potassium-free diet. There's actually no way that you can get all the radioactivity out of the human body. So what we do instead is we put PPE on ourselves. so we will be wearing like a mask and a face shield and so on. And then even the clothes, there's no way to get entirely to zero radioactivity, but they are made out of a material that is as close as possible to being totally inactive.
Awesome. And I think we have one final question here. Why is it so difficult to research matter and atoms?
Well, there's a few different reasons. So one issue about researching matter is that, well, as I said, not everything in the standard model interacts with light, in particular, not with visible light. So there are, for example, other parts of the electromagnetic spectrum that we can't see with our eyes. So we need other apparatus to pick it up for us. And then there's also particles that are unstable. So for example, other flavors of quark, you can produce them in an environment like a super collider, but then they only last a very, very, very short amount of time before they spontaneously turn into other particles that are stable. So in order to not only produce these unstable particles, but also get a glimpse of them before they go poof, is really not easy. And then, as I said, just to have enough energy in the super collider to produce them in the first place. So it was not until the Large Hadron Collider that we actually had a super collider energetic enough to produce Higgs bosons.
Well, thank you so much, Professor Diamond. This was a great presentation, and I know I will definitely look forward to hopefully looking at the Snow Lab in VR. That would be very fun.
Awesome.
Thank you so much for your time today, and thank you again for your presentation.
Okay.
Have a good day. All right. And we are now on to our last presentation for webinar 3 today. And this presentation is given by the Donnelly Center for Cellular and Biomolecular Research. And our activity is entitled The Power of Yeast. And one last time, please remember, if you have any questions for our speakers, you can post them in the Zoom chat and we will answer them if there is time. Please take it away.
Hi, my name is Sylvia, and today me and my lab mates Irvi and Clarence are going to be talking to you about the awesome power of yeast genetics.
Welcome, folks. Today we'll be talking about a small but powerful organism that has been crucial in numerous scientific discoveries of the past few decades: yeast. The most commonly used species of yeast today, Saccharomyces cerevisiae, is actually one of the oldest domesticated species on Earth. For thousands of years, it has been helping humans make bread and alcohols, such as beer and wine. You see, yeast chews up sugars it finds and releases carbon dioxide, a gas which makes bread rise, as well as alcohol.
To date, there are about 1,500 species of yeast that are recognized, but there are probably even more out there that we just haven't discovered yet. Now, yeast is an essential part of our ecosystem and can be found absolutely everywhere. It's on fruits, vegetables, soil, in the air that we breathe, and even our guts. But what really is yeast? What does it look like? Well, yeast is a single-cell fungi. We as humans are multicellular, meaning that our bodies contains trillions of cells that work together to keep us alive. In contrast, yeast is unicellular, meaning that one cell contains everything it needs to survive. Now, yeast is really, really small, but it's also really powerful to study. One yeast cell is about 5 micrometers wide. Now, to put that into comparison, a human hair is around 80 micrometers wide, which means that around 16 yeast cells can fit across a single human hair. How cool is that?
As biologists, we want to understand how the human body works. This is important because by understanding more about how our body works, we'll be better able to help people when they get sick. However, studying human beings themselves is not practical. We need a simplified model system which is easy to experiment with. This is why scientists have turned to yeast. First of all, yeast is extremely easy to work with in the lab. Yeast is small, so it doesn't take up much room, and it grows very fast, which allows us to do many experiments really quickly. Yeast cells grow up to form colonies that we can see with our naked eye after 2 days, and each colony contains around 100 million cells.
But perhaps the most useful feature of yeast to a biologist is how closely related it is to humans. You might not think you have much in common with a yeast cell, but your cells are actually remarkably similar to yeast. In fact, yeast is a fungus, and fungi are more closely related to humans than they are to plants. Inside every cell on the planet is an instruction manual called DNA, which contains the code to make all the building blocks that organisms need to survive. The DNA code of yeast is very similar to the DNA of humans. DNA is divided into units called genes, and genes contain the instructions that tell the cell how to make proteins, which are the building blocks of the cell. Human beings have about 20,000 of these protein-coding genes, and yeast has about a third of that, about 6,000 genes, which isn't a huge difference. Also, there is a human version of more than 60% of all yeast genes. Additionally, the way that yeast cells operate is very similar to that of human cells. How the cell ensures that its DNA is copied and passed on to future cells, how energy is produced, how the cell responds to environmental stressors, how the cell makes all the materials it needs to survive. All of these processes are extremely similar in yeast and in human cells. Scientists thought it was so useful of an organism to study that in 1996 it was the first eukaryotic organism ever to have its genome fully sequenced.
Now, there are 4 Nobel Prizes awarded for discoveries involving yeast research, which is quite an impressive amount for a single organism. In 2001, Leland Hartwell, Paul Nurse, and Tim Hunt all shared the Nobel Prize for establishing the roles of different genes in controlling how a cell divides. Now, this is an important piece of scientific work because it told us about the different machineries that are needed in order to make sure that a cell just doesn't just stop dividing or divide like crazy. Now, Hartwell identified over 100 genes that are involved to making sure the cell divides properly. He found that there were 2 classes of genes that control how a cell typically divides. The first class are genes that normally tell the cell to divide when it's safe to do so. And the second class are genes that normally tell the cell not to divide when it's not safe to do so. However, in cancer cells, this program is completely messed up, and they don't behave like they normally should. So in the first case, they kind of act like accelerators in a car that are constantly on and just don't stop. And in the second case, genes that are supposed to tell the cell to stop dividing don't work. So this is kind of like malfunctioning brakes in a car. And these discoveries have contributed massively to understanding how cell division is controlled in cells. At the same time, it really helps us understand what goes wrong in cancer cells.
Yeast as model system has also been very helpful to find out how things are moved across a cell. In 2013, Randy Shakeman shared a Nobel Prize for his contribution in discovering the genes that are essential for moving things around in our cell, a process known as vesicle trafficking. Randy Shakeman used yeast with different mutations to find out which cells had problems in their transport system. Over his career, he found nearly a dozen genes that play key roles in vesicle trafficking. In 2016, Yoshinori Oshumi was awarded the Nobel Prize for his groundbreaking discoveries in mechanisms of autophagy. The literal meaning of autophagy is self-eating. It was difficult to study this process in human cells. Oshumi found a way around this problem by using baker's yeast to study the process. In a series of brilliant experiments, Oshumi identified genes that were essential for autophagy in yeast. He went on to show that a similar mechanism is used in human cells. His discoveries opened the path for understanding how cells recycle its content and its importance in many physiological processes, such as adaptation to starvation and involvement in disease.
In the Boone and Andrews labs, we too work on the model organism, the budding yeast. Now, in science, what we often like doing is to systematically take things away one at a time and ask what the effects are. And because yeast is such an easy organism to manipulate, scientists asked if the cell lives or dies when you delete its genes one at a time. This resulted in the construction of the deletion collection, where scientists would delete genes one at a time and ask whether deleting that gene alone had any impact on the cell's ability to live or die. They found that in most cases, approximately 80% of genes do not affect a yeast's ability to live. What this told us is that its genome is highly buffered, meaning that there are redundant backup plans for a cell. This makes sense, because a cell has to have alternative strategies that help it stay alive. Otherwise, if there are no reinforcements, a cell can quickly succumb to different harmful signals in the environment or the natural errors during cell division.
In our lab, we wanted to use this deletion collection to ask what happens when we combine two mutations together. This means that we want to systematically look at the effects of combining mutations in gene 1 with gene 2, gene 1 with gene 3, and so forth until every single combination is achieved. As you can imagine, this is a very tedious effort and required elegant and effective strategies to carry out this highly demanding task. So towards this goal, we developed high-throughput technologies that uses robotic manipulation to systematically generate a large set of combinations. Each robot can handle hundreds of plates that contain hundreds of thousands of unique combinations in a given day, a scale that was unprecedented and still is for systematic screenings. Over the past 10 years, we have been able to survey almost every double combination that exists in the yeast genome to ask how the combination of different gene mutants alter a cell's ability to live. This resulted in the creation of what is known as the yeast genetic interaction network. What this network is that each of the dots shown in this blob here represents a gene, and the distance between each gene represents how similar it behaves to another gene shown on the map.
Now, to illustrate the value of building these networks, we want to highlight a finding using this technology. We want to tell you some of the insight we gained with the Shwachman-Bodian diamond syndrome when we teamed up with another scientist in the UK. This disease results in bone marrow failure and predisposes an individual towards leukemia, a type of blood cancer. Now, we used yeast as a model organism because the gene that causes the disease normally in humans is also present in yeast. And what we were able to find is that when you combine changes in another protein, this rescues the cells from becoming very, very sick. Now, normally, the gene that causes the disease participates in a process called translation. And translation is the process by which machinery in the cell gets made and is essential for the cell to function. Typically, this process of translation has to be tightly regulated because you don't want the cells to make extra machinery that gets wasted or too little, otherwise the cell cannot function. Now, the changes in this protein called TIF6 rescues the defect in the disease gene by changing how tightly that protein hugs onto that machinery. And why this is interesting is because if we can find patients who have mutations in that disease gene in humans, we can start to develop therapeutics that mimics the effect of TIF6 such that we can take some of the findings in basic science and translate that to the bedside.
In this project, we were trying to look at how every single protein in the cell, and these are the building blocks of the cell, changes in response to some sort of insult.
Life is a dynamic series of events, and from a cell biology perspective, proteins are a dynamic component of how cells work. If we understand how proteins move and how they change in abundance, those are the things in cells that make all the action happen. Just like a house has different rooms, cells have different compartments with different roles, like holding DNA, producing energy, or getting rid of waste. Each cell has thousands of genes, which make thousands of proteins, and proteins are the building blocks of life. In this study, we looked at where proteins sit in the cell to find clues about their function. For example, proteins that share space with the DNA can help interpret genetic code. Some proteins move between compartments when the cell receives a signal from the outside world.
So that signal might be grow, divide, stop dividing. And so in order to make that happen, the cells will move proteins around, shift around their building blocks. And so it's really important to understand how that happens if we're going to be able to understand why cells are healthy and why they're sometimes diseased.
If we can get a firm hold on that, then we can actually start to really model how different networks of proteins are having an impact on what a cell looks like, how a cell behaves, how a cell responds to environmental stress, and maybe how a cell goes off its normal path to become a disease cell.
Now, we hope that we were able to illustrate to you the awesome power of yeast genetics and the immense amount of work that goes into studying basic scientific questions. Science is really a concerted effort of many scientists, public funding, and ongoing support to fuel important discoveries that, even though seem really basic, carry large implications for our health and disease. And we hope that the next time you eat a piece of bread, you're inspired that it isn't just to feed our stomachs, but to feed some very important scientific discoveries as well.
Okay, thank you. Sylvia, did you have anything you wanted to add before we go into a few questions?
No, not really. I'm just really excited to talk and answer everyone's yeast questions. So let's just jump right in.
Sure, and thank you so much. That was a great video. I loved it.
Oh, thank you. Yeah, I'm really proud of the team. I'm the one representative, but obviously it was many people worked together to make this video, and unfortunately they couldn't be here today as well.
Well, that's too bad, but thanks. It's great. So first thing, hopefully it's a nice and easy question. What is your favorite thing about yeast?
Oh my goodness. I think my favorite thing about yeast is probably just how easy and fast the experiments are, because sometimes I do experiments with other organisms like human cells, but the data takes months and months and months to come back. But then when I'm working with yeast, it's just so quick and easy and turn around, and you get that really quick satisfaction of your experiment working. And also, the lab kind of always smells like bread, so that's nice. A nice like toasty environment to come into every day.
I like that. I like that
Yeah.
a lot. Sounds like it would just smell like home.
It's nice. We even sometimes use our own yeast in the lab that we culture to brew batches of beer as a lab together.
Very cool.
It's another fun perk of working in a yeast lab.
Sounds like it. A little bit of a follow-up question on that. We have a question here. What exactly do you study about yeast?
Oh, I actually, my main PhD project is no longer in yeast. The project sort of took a different direction based on the data, and now I work only in human cells. But when I started out, I was like in yeast and in human cells. So I study a very particular disease called NGLY1 deficiency. And in the video, we talked about how yeast can have like its own version of human genes. So the initial idea was that this gene, it basically, if you don't have this functioning version of this gene called NGLY1, you're very sick. And yeast has a version of that gene called PNG1. So I was trying to study its function in yeast just because, like I talked about, it's just such an easy organism to work with. The experiments are quick, and there's just this wealth of genetic tools that make it a lot easier, and then that could inform the human research. But it just sort of now, it's a human disease, so we eventually just moved the entire thing into human systems. So I haven't worked with yeast in a few years, but I do miss it.
Yeah, of course. One of the videos mentioned that about 80% of the genes were not necessary for survival. What are they for? Do we know?
Okay, yeah. So one idea is that they're just buffering other genes. So if you have two genes that do a particular function, there's a backup copy. Because sometimes, even in healthy yeast cells, when they replicate, that replication in DNA can produce errors. It can copy it wrong. And then in that case, you're really lucky that you have a backup. So it's just good to have all these backups in case one gene fails, the cell doesn't die. It can rely on these backup systems. And another hypothesis is that they might not be necessary in the conditions that we're using them in the lab. So when we do these screens, they're in, we take very good care of them. We give them lots of nutrient-rich food to eat. They're not really stressed out. They live this very cushy life. But perhaps not like when they're out in the wild, it's not as cushy. We're not as like nice to them as we are in the lab. And they could be necessary, for example, certain stressful conditions that we just haven't tested in the lab yet. So some genes might be necessary when it gets really hot, or when it gets really cold, or when it gets really acidic, or when there's like an imbalance in the nutrients. So those are probably necessary in certain conditions that we just haven't tested yet.
That makes sense. And a follow-up question to that was, would we expect that trend to be similar in human cells?
Yes, actually, human cells are also highly, we say it's buffered, meaning that there's multiple genes that do the same function. So yeah, we do see a lot of these, like humans have multiple copies, which is really great for us as human beings. You know, our cells are quite resilient. It makes my job a little more difficult in the lab because sometimes I want to study what a gene functions is, and I try to like attack it so I can see what goes wrong. And then some other gene takes over and the cell looks fine. And I'm like, no, that's making my life harder. But I know that these systems are in place to keep me alive. So I feel like I can't complain too much.
Yeah, I would think so, but that does sound quite frustrating.
Yes, yeah. Your body has evolved to protect you.
And thank
And
goodness for
there's
that.
multiple layers and multiple reinforcements for that.
That's great. Oh, we have another question from an attendee here. Is yeast the only model organism we use to study? Are there others you know of?
Oh, yes. So there's a few. Well, There's a few that are very famous and a few that have a few, like really emerged and a lot of scientists work on. So a few, like the ones that come to mind, there's the nematode worm C. elegans. And I actually did 3 years of research on worms when I was in my undergrad. And they're about 1 millimeter long, and they're transparent, so you can see what's happening inside them, which is a very useful tool. And how their neurons connect in their brain is conserved from one worm to another. So it's a very useful tool for neuroscience research. And there's also fruit flies are a very commonly used model organism. There's actually 100 years of fruit fly research that has existed. And because it's been used for so long, there's all these really great genetic tools. People also, including myself, use cancer cell lines, which we can grow in dishes on plates. There's also a plant, some plants, some bacterial cells such as E. coli. So yeah, there's a few of them. And the way that we as scientists choose which one to work on is highly dependent on the questions that we're asking. So if you're really interested in like development in neuroscience and you want to understand how different systems of the body interact, you might want to look at a fruit fly or a worm, because, you know, they have multiple systems. You know, they have digestive systems, they have nervous systems, they have, you know, some version of a skin. You know, you can look at all this development and you can see how they go from an egg to a full adult. So like, that's really useful. What our lab is really interested in, like what is happening inside one cell. We don't really look at how different systems of the body interact. We just like are zooming in inside one cell. So that's why we use yeast, because it's a unicellular organism. And then you can sort of really focus in on your question with that. So that's how, as scientists, you would choose what to work on.
That was a great answer, and thank you for providing us with all of those very cool examples.
Yeah.
We have another question here. It's a bit of a two-parter. Did the genes of the same function double that function, or only one is activated? How does it make sure only one is activated?
Yeah, so that's a really good and kind of complicated question. And that's, in fact, such a good question that that's actually a major topic of research in our lab. So we're working on it, but basically we think that it's a case-by-case basis. I can't make a sweeping statement for all genes. So there are some genes where like you actually need, you know, multiple copies functioning to have a certain high enough level, but those like of product of those building blocks of whatever it codes for to keep the organism alive. But for the most part, the cell can even like regulate the expression of one or the other. So we see if you have two genes that do the same function, and then one gene, like, you know, there's an error in DNA replication, there's an insult, it's no longer functioning. The cell sometimes can detect that and then upregulate the other one in compensation. So they work really hard to keep us healthy, our cells. But yeah, it's a gene by gene basis.
That's very interesting. Mm-hmm. And we have a question here. What else can yeast be used for? I mean, we already talked about brewing beer.
Brewing beer and wine and bread. So yeah, like outside of the realm of cooking and fermentation, like other kinds of research that go into it, it was really instrumental historically in working at like really basic cellular biology pathways. So like right now, we're in the last part of the video, we're talking about how genes interact like with each other, and we're looking at the scales of networks. But historically, it was really used to work out some of the basic like biological pathways that your cells use to keep you alive. So how the cell, how the DNA, which is that like instruction manual in the cell that codes for all those building blocks, that has to be copied as the cell divides. You know, you need to make one new copy of the DNA and one copy of all of the little machines inside the cell. So like working out how those pathways were first discovered, a lot of that research was done in yeast. And a lot of the research of like how we get from DNA as a starting point to protein, it's quite an elaborate process. So like a lot of the mechanisms of that was worked out in yeast as well. And really just like most of like the basic biology that we know, a lot of it was worked out in yeast.
Awesome, that's very cool. I have a few last questions for you. If we have a missing gene, does that mean that cell is unfunctional? Does it become a cancer cell?
Oh, that's a really great question. So in a nutshell, it really depends on the gene. So, you know, if it's a gene that's highly buffered and we lose it, it might not have any effect at all. But there are some genes, which we call essential genes, which you absolutely cannot do without. And if you lose that, then the cell just dies. And so yeast, there's 6,000 genes total, 1,000 of those, so 1/6 are essential. So you absolutely can't do without those. And then going into human cells to address the cancer portion of that, whether a cell, if you lose a gene, whether that loss determines if a cell is going to become cancerous is highly dependent on what the identity of that gene is. So it doesn't apply to all genes, but there are certain genes that really control and tightly regulate how often the cell proliferates, how often it divides and creates new daughter cells. And cancer, by definition, is just uncontrolled cell growth. So if you lose a gene that is responsible for making sure that the cell doesn't divide when it's supposed to, then that could become cancerous. And that is like a minority of cells. And to go back further about essential genes, there's only about like 2,000 essential genes in humans out of 20,000, so about 10%. So, you know, case by case basis again.
Great. We actually had a follow-up question from that. Do we have replicates of those essential genes?
So by definition, no, because the way the term essential gene is defined is that if you knock it out, the cell dies. However, there are copies of genes, which we call paralogs, and those, you know, you could have two paralogs that do similar functions, and they're just basically a copy of each other, and they're in the same genome. And if you delete, and it's again a buffering situation. So if you delete one, the cell lives. Then if you delete both of them, the cell dies. So we wouldn't call each of those genes essential, but we would call the pair of them like a synthetic. We have a term for this. It's called like a synthetic lethal pair. And actually, my lab was instrumental in trying to find all of the synthetic pairs in the entire yeast genome. So we can trace back and we could be like, oh, these two are essential. Like one is essential in the absence of the other. So in that way, it's like, it's a conditional sort of essentiality. So it gets very jargony at this point, and these are just the terms that scientists have associated to all of these. But yeah, that's the basic idea.
No, that's great. And we have a question here. Is a yeast cell structured similar to a human cell? Do they have organelles?
Yes, they do have organelles. So for the most part, it is very similarly structured. A key difference between yeast and human cells is actually the membrane. So on the outside, human cells just have this phospholipid membrane, but on top of that, the yeast cells have this hard coat called a cell wall, and that's basically made of sugars, and it just it gives it a little bit more structural integrity, which is probably important because they're often found, you know, in dirt and in soil and being eaten, and it sort of prevents them from, you know, from the weather, from acids that are found like on the surface of the fruit that they're on. So they're a little hardier, but then zooming into the inside of the cell, all the organelles, all the basic organelles are the same between yeast and humans. You know, we both have nuclei, we both have mitochondria, endoplasmic reticulum, Golgi. We both have versions of like the vacuole. So it's like highly, highly, highly similar. Humans just have like a few more specialized one, but all of the basic ones are there.
That is very cool. I like it. And our last question for you, what is next for yeast as a model organism? Are there any emerging lines of research?
Oh, wow. So I guess one emerging line of research is the invention of CRISPR is this very powerful technique that we can use to genetically modify organisms. So a lot of people are applying that to yeast right now. That being said, I didn't directly answer your question. That's not really a direction, that's more of a tool, but it will sort of enable us to fill in the gaps in some of the existing research. But as a field, if I had to speculate where it's going, I think as the field of genetics, you know, sequencing our genomes and learning more about sequencing is really a direction that the field of genetics as a whole is going. And we're learning at an unprecedented rate more about the genetics of disease, because as sequencing of entire human genomes becomes cheaper and cheaper, we have better and better ideas how to pinpoint, oh, this person has a disease, it's probably caused by that gene. And then from there, because as I mentioned, yeast is such an easy organism to use, we can start using yeast to sort of understand the function of these disease genes more in depth. And there's very cool techniques where you can like sort of take the particular genetic anomaly in a gene, in a disease gene that a human has, and then recreate that in yeast in order to better understand exactly what's going on if a person has this disease gene. So yes, definitely applicable to like very specific disease cases is I think where the field is heading.
That sounds very exciting. And we just like to thank you once again for joining us today, and to the rest of your lab for the wonderful video. Thank you.
Thank you so much. It was a joy to participate in.
Thanks. Have a good day.
You too. Bye.
Okay, so thank you again to all of our presenters today for their wonderful presentations. We will now move on to our closing remarks, and we invite you to join us for a keynote presentation following this webinar that we will host in a separate Zoom link. Next slide, please. Just before we do, we would like to remind everyone that Science Rendezvous also hosts a Sci-Art gallery, a space to appreciate the beauty and creativity in science. As we are unable to host an in-person gallery this year, we've made a virtual one on our website. Just click on the 2022 festival and then Sci-Art gallery to check out all of these fun things. Next slide, please. We would also like to extend a huge thank you to our SR exec team for their dedication to this year's event. Without them, this year's virtual SR 2022 would not have been possible. Next slide. And lastly, we would like to thank you for attending the SR 2022 virtual festival, and we look forward to seeing you again next year. For updates on our events, follow us on our social medias at U of T SR. We will now have a special keynote by Professor Dwayne Miller, founder of Science Rendezvous, at 4 p.m. in a new webinar, who will be presenting his talk, What is Life? Can we measure it? Please join us in this new link for his presentation. You can also find this link on our website in the program schedule. We hope to see you there shortly, and thank you once again for attending SR 2022.